to send humans to the planet. The volunteers, who are not astronauts, are expected to enter the environment called a habitat in June. It was built at a major research base at NASA's Johnson Space Center in Houston. During their stay, crew members will take part in many different activities, NASA said in a statement. This will include taking part in simulated spacewalks, doing robotic work, caring for the habitat, exercising, and planting crops. The 160-square-meter habitat is also designed to recreate environmental pressures that future visitors to Mars could face. Examples of this will be carrying out activities with limited resources, being isolated, and experiencing equipment failures, NASA said. The simulated environment was built using 3D printing technology. 3D printers have been used in recent years to build increasingly large structures, including entire homes. The Mars habitat is part of a NASA program known as the Crew Health and Performance Exploration Analog, or CHAPIA. It is expected to include a total of 3 simulated environments. Grace Douglas is the lead researcher of the CHAPIA experiments. She told the French news agency AFP that NASA has been looking at 3D printing technology as a possible way to build habitats on other planetary or lunar surfaces. NASA officials are still in the early stages of preparing for a mission to Mars. However, most of the agency's current efforts support upcoming Artemis missions, which aim to return humans to the Moon for the first time in half a century. While in the habitat, NASA workers will continuously follow the volunteers' physical and mental health. With that data, NASA will be better equipped to study how astronauts can learn to use only the resources they have, Douglas said. We can really start to understand how we're supporting them with what we're providing them, she said. And that's going to be really important information to making those critical resource decisions, she added. The habitat includes an outdoor area that simulates the Martian surface and environment. That area, however, will still be within the simulated environment. The volunteers who will take part in the first experiment have not yet been named. NASA says the process of choosing the individuals will follow the same guidelines that are used to choose astronauts. The team members will be expected to have rich backgrounds in science, technology, engineering, and math. In addition, only American citizens or permanent U.S. residents can be chosen. Interested individuals have to be between 30 and 55 years old, in good physical health, and have no dietary issues or motion sickness. Former Canadian astronaut Chris Hadfield told the Associated Press in 2021 that he thinks the requirements show that NASA is looking for people who are close to being astronauts. That, he noted, is a good thing because it will make the experiment better. A past Russian effort to create a simulated Mars environment called Mars 500 was not highly successful, Hadfield said. This is because the people involved were too much like everyday people, he added. For the right person, this could be great, Hadfield said. He spent 5 months in orbit in 2013 at the International Space Station. Just think how much you're going to be able to catch up on Netflix, Hadfield joked. If they have a musical instrument there, you could go into there knowing nothing and come out a concert musician, if you want, he added. I'm Brian Lynn.
Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 285, Return of the OREX. I'm Gary Jordan, and I'll be your host today. On this podcast, we bring in the experts, scientists, engineers, and astronauts, all to let you know what's going on in the world of human spaceflight and more. Asteroids are a fascinating presence in our solar system. So much so, in fact, that NASA and other space agencies around the world have been observing and exploring them for decades to unravel their mysteries. We can learn quite a bit just from looking at them, but sometimes we have to take it a step further. Take the DART mission, for example, the Double Asteroid Redirect Test, where we intentionally crashed a spacecraft onto an asteroid to measure its change in orbit as a planetary defense test mission. On its way back to Earth as we speak is a mission called OSIRIS-REx, or Origins, Spectral Interpretation, Resource Identification and Security, Regolith Explorer. This spacecraft launched in 2016 to rendezvous with an asteroid called Bennu in 2018. Bennu is a particularly interesting asteroid. I'm not a scientist here, but it has something to do with potentially unlocking the secrets of origins of life in the universe as we know it or something. I don't know. Doesn't sound like that big of a deal, but there are a few scientists around the world that think that this is a pretty important thing. Not only is Bennu itself pretty interesting, but the OSIRIS-REx spacecraft didn't come to an explosive end like DART. No, this spacecraft had a more gentle arrival at this particular asteroid, so it can take pieces of the asteroid with it on a trip back to Earth. With actual samples of the asteroid in tow, there are seemingly endless ways that scientists can use powerful, earthbound instruments to help humanity uncover the secrets of the universe. OSIRIS-REx is not scheduled to return to Earth until September of this year, 2023, but as you might expect, there's a ton that's happening behind the scenes in anxious anticipation of the spacecraft's return. To help us understand more about this mission, the anticipated science, and the preparations needed before OREX touches down in the American desert, we have the mission's Deputy Project Manager, Mike Moreau, and the mission's lead curator, Nicole Lenning. All right, let's get to know this mission. Enjoy.
T-minus 5 seconds and counting. Mark. Mission start. Launch commit lights are correct. There she goes.
Houston, we have a podcast.
Mike and Nicole, thank you so much for coming on Houston. We have a podcast today.
I'm really excited to talk about OSIRIS-REx with you today.
I'm happy to be here. Thanks. It's great to be on this side of the microphone.
Yeah, I love that we get to be in person for this one too. Mike, it's really lucky that you were here. You're in Houston, but you're based in Goddard, I believe. So what are you doing here this week?
Yeah, so I came out to meet with some of the folks at JSC that are supporting OSIRIS-REx. Cool. They're doing some of the analysis that we need to look at as the sample capsule comes back to Earth. We are doing all this public risk assessment and safety analysis to make sure that all the things that could go wrong, everything will still be safe. So.
Yeah, it's not like the work is beginning when OSIRIS-REx comes back and lands in the American desert, right? This has been a very ongoing thing.
Yeah, well, of course, the team was super busy, when we had the mission, arrived at Bennu and right. did all the early characterization. And then it kind of settled down for a little while as the spacecraft's been making its way back to Earth. But now things are starting to pick up again as we get ready to get the sample back home this year.
Definitely ramping up. Yeah, this is very exciting. I'm happy to have you both here today. A very exciting year. OSIRIS-REx is coming back. Very cool samples. We've talked about OSIRIS-REx a couple of times on the podcast. Actually, funny enough, we talked to some experts before OSIRIS-REx reached Bennu, and then after it was coming back from Bennu. So this is we're still going to lead up to it, but we haven't really dedicated like a full episode to it quite yet. So I wanted to go kind of deeper into what OSIRIS-REx is and why this mission is so important, why Bennu is so interesting. But first, let's start with you because we have two, of all the people we could have picked to talk about this, I'm very excited to have you guys. Mike, if we'll start with you, because you've been with OSIRIS-REx for quite some time, and now you're in a more, you got a bigger role with the mission. Can you tell us about sort of your journey that led you to where you are?
Sure. So I've been with the mission almost 10 years now. It takes a long time to do one of these planetary missions. So I joined the project in 2013 as leading the navigation team. And we can talk more about this later, but there were a lot of interesting navigation challenges with this mission, going to a small body like Bennu and trying to navigate your spacecraft all the way down to the surface. So that was an exciting challenge. Did that for several years. And after the spacecraft launched, then I moved into a role on the project management team. So I'm the deputy project manager at Goddard in an organization called Space Science Mission Operations, where we operate a bunch of NASA spacecraft, and OSIRIS-REx is one of them. So I focus on OSIRIS-REx. And now, as we're getting ready for the sample to return home, I'm going to be the recovery manager for NASA. So I'm working with our partners at Lockheed Martin and with some of our colleagues at the Department of Defense and then Johnson Space Center to do everything we need to do to prepare for the sample to come home. So your
job sort of switches as the mission goes on. You get new titles as you get to different phases. That's cool.
It's been interesting, and it's nice to be here at JSC. I spent a lot of time, maybe 10 years or so ago, working Constellation program and doing some human space flight support. So it's been great to walk around the halls here and meet with some of my colleagues that I haven't seen in quite a while.
A bit familiar. Well, welcome back. It's good to have you. This particular role, the deputy project manager, what is sort of the main things that you look over now?
Well, we have there's several major partners on the team. The folks that are operating the spacecraft are at Lockheed Martin in Denver, and then there's a small team called Kinetics that does the navigation in conjunction with our Goddard folks. And of course, the science team is led by the University of Arizona. So as the mission management at Goddard Space Flight Center, we coordinate across all of these groups. We make sure that they're getting the funding they need to do the work and planning all of the work. As we get ready for sample recovery, there's some new team members that come into play. Nicole's part of our curation team here at Johnson Space Center, and they're preparing to receive the samples. And as I mentioned, we're working with both the Air Force and the Army because the sample comes back to this military base in Utah called the Utah Test and Training Range. And so they are going to help us with all the logistics of the recovery of the sample.
So you're seeing a lot more of the mission than you said you started 10 years ago, and I know you were in navigation mostly, but now you get to touch all these really cool pieces. You get probably a much wider perspective in this role.
Yeah, I really do get to see the whole mission and work with all the partners, and it allows me to talk to people in the public about the mission, and I enjoy that.
Great.
As well. So.
Well, that's what this is all about. Happy to have you here, Mike. Thanks. All right, Nicole, deputy curation. That's pretty cool. So what led you to this role for OSIRIS-REx?
So for me, I'm joining at a later stage than Mike. I joined in 2020, and I came from studying asteroids as a geologist and as a sample scientist, specifically through studying meteorites and a combination of also working in curation at the Smithsonian. So when OSIRIS-REx was selected, it was before I got my PhD. I was working in collection support at the Smithsonian, and I remember hearing about it and being like, it's going to come back in 2023. Where am I going to be now? And so it's so cool to be part of it. And in the process of studying meteorites, I, for my PhD, studied meteorites that we think are regolith samples from Vesta, so that intersected with the Dawn mission quite a bit. And then I had been applying to a bunch of our meteorites that we study and that I've studied come from Antarctica. And so I applied to be part of the field team member. And actually, just after I interviewed for this job and before I started it, I got to go to Antarctica as part of NASA's field team that collects meteorites in Antarctica. So most of which are asteroid samples, but they haven't been protected in the way we're going to be able to protect this sample.
Okay, so it's like, it seems like OSIRIS-REx has always had sort of a place in your heart, and you've taken these incremental steps. I'm sure like Antarctica was like a pretty decent step to get you sort of where you are today as well, right?
It definitely was great to be able to collect meteorites and really think about how the environment can affect them, right? They pass through Earth's atmosphere. And into Antarctica, it's a dry desert, very low humidity. It's really the best place a meteorite can fall from a scientific perspective, but there's still a lot of terrestrial contamination potential growth of things like sulfates on the meteorites, where our sample will much better be able to constrain and know if we find something like a sulfite in a sample that we've had that whole chain of custody on. It's very promising that it actually came from Bennu, rather than that sulfate growing in a terrestrial environment from a found meteorite.
So safe to say in the scientific community, this sample that we're going to be talking about today is extremely valuable.
I would definitely say that, yes.
Awesome. How was Antarctica, by the way? I think Antarctica, and the first emotion that comes to mind for me is fear. But I wonder, how it was for you.
It was incredible. I loved it. I had wanted to go. I did talk to lots of other people who went, and I started out wearing the maximum quantity of clothes. So I was wearing 6 layers of long underwear, 2 pairs of snow pants, plus the big red. And then when I got too hot, I would take off clothes, which I definitely recommend that for people in the deep field in Antarctica. Don't let yourself get cold. Just wear all the clothes. Just be a giant, puff marshmallow person.
Love it. Okay, well, I'm glad that it led you to this role. I definitely want to. We're going to explore more about what we're doing in terms of curation, what we're doing to prepare for OSIRIS-REx. But for our listeners, let's sort of set some context. We keep bringing up these things, OSIRIS-REx and Bennu. These are sort of like the overall thing. Mike, I guess we'll pass back to you. Let's start with the asteroid. Let's start with Bennu for a bit. What the mission was headed for this particular thing. What is this asteroid and why is it so interesting?
So near-Earth asteroid Bennu is about 500 meters in diameter. It was about the height of the Empire State Building. Seems like a pretty big object, but it's actually the smallest object that's ever been orbited by a spacecraft before. And that made it an interesting target because there's a lot of operational challenges of doing that. But Bennu was picked for this mission for some very specific reasons. It's a carbonaceous asteroid. We believe that the material that it's composed of is some of the earliest building blocks of the solar system. So by bringing that back to Earth and studying it, we can learn a lot about the early formation of the solar system. And Nicole probably has more to say about some of that. But it's also an interesting target because it's one of the most potentially hazardous asteroids that we know about. It's a near-Earth asteroid. It's in an orbit very similar to the Earth's orbit around the sun, so it actually crosses the Earth's orbit, and it has like a 1 in 1,700 chance of impacting the Earth late in the 22nd century. So it made it a very interesting target to study, so we could characterize its orbit around the sun better and have a better prediction of that potential hazard in the future. But finally, there's very few asteroids that are both accessible, meaning we can get a spacecraft there and also get it back to Earth. And we had to have that, two-way journey in order to bring the sample back to Earth. And all of those things in terms of the size, its composition, what its orbit was, we had maybe 5 or 6 asteroids to pick from that were lining up with the time we were doing the OREX mission, and Bennu was the best choice among those. So.
Wow. Were any of the other 5 carbonaceous?
I don't know. Do you know the answer to that question, Nicole?
I think they were. I think the mission,
couple.
because we wanted to look at the building blocks of life, prebiotic compounds, and carbonaceous.
Naturally, that was like one of the
yeah. So I think
criteria.
that was one of the narrowing down.
An interesting point is that one of the other targets we were considering is the target of the Hayabusa 2 mission. Ryugu was one of the candidates, and it just because it's in the same time frame, and it was also just met a lot of those criteria. So.
Okay, yeah, I think considering other missions too, that makes a lot of sense. Well, I threw out the term carbonaceous because I think it's a pretty important term in terms of Mike was talking about the building blocks of life. I think that's a pretty important element to what makes Bennu so special. So what is carbonaceous? Like what is it that exactly we're looking for that's going to help us find these really important questions, search for these important questions?
So for the carbonaceous aspect, the part of that carbon that we're really interested in is things that, were carbon-based life forms, amino acids, things like that. So even though Bennu is a very inhospitable place for actual life, it's a good way to preserve those building blocks of life because there isn't anything that can survive there to eat those things and use them. And carbon is a really essential compound in all of those elements. And where we don't tend to see carbon in as much abundance in the non-carbonaceous chondrites and the asteroids we associate with them as well, but it is the form of carbon. There can be, you don't want something like a graphite, inorganic carbon. You want to ultimately find amino acid-bearing sample material, and the carbonaceous chondrites are the best target for that because you tend not to have or have very, very low abundances of the organic carbon compounds in other meteorite groups.
Excellent. So sort of expanding on that in terms of, Mike was talking about maybe the origins of the universe, but it sounds like it could be the origins of life as we know it.
Yeah, they definitely could be the building blocks of life in our solar system, either on Earth or potentially elsewhere.
This is big. This is a very, very important questions. And OSIRIS-REx was the way to, was the mission, was the spacecraft to go to this very special asteroid. Mike, tell us about OSIRIS-REx. What makes this spacecraft and this mission so special?
Well, yeah. So the primary objective of the mission was to collect a sample from an Earth asteroid, return it to Earth, right? But in order to do that, we had to do a lot of other pieces of the mission. And OSIRIS-REx had the objective of characterizing this object in great detail in order to just understand the object and the context of the sample that we were collecting. Those very detailed observations, which are imagery and spectroscopy and topography data. All of that is very useful because it can be a calibration point for the telescopic observations that we make of asteroids from the Earth. So by studying it up close, comparing Earth-based observations, we're able to get like a truth marker for what we're seeing from Earth-based telescopes and understand other objects that we're seeing from the Earth better. So that's an objective of the mission. But as I mentioned, because it's a hazardous asteroid, we also wanted to track the orbit of Bennu very precisely by having our spacecraft orbiting Bennu for 2 years and all of the Deep Space Network tracking data from that. We were able to refine Bennu's trajectory very precisely and update those potential hazardous impact calculations. And then once we collected the sample, we studied the sample site in great detail to provide the context. You know, what is the composition of the material that's there and how was the material laid out? And that provides context for the sample that's collected. So all of those objectives formed the scientific objectives of the mission, then drove the observations that we collected and the orbits that we flew around to get these observations and eventually collect the sample. But that is OSIRIS-REx in total, is all of those objectives.
So it sounds like a lot had to be loaded onto this spacecraft. You talked about a lot of different instruments, and then there's this very delicate piece of actually grabbing something from the asteroid itself. So in terms of the design of the spacecraft itself, the different components, what goes to the asteroid, what goes down and actually touches it, what comes home? What are the different
and I
pieces
should
there?
talk more about the spacecraft. It's essentially this robotic explorer. It has a series of cameras. It has a LiDAR instrument and other sensors that we use for navigation. But it also has some unique capabilities. It has a sample return capsule. So that's something about the size of a small dinner table that might sit for 3 or 4 people around it, like a round table. That's the only part of the spacecraft that's entering the atmosphere. The spacecraft itself is the size of like a 15-passenger van or something like that. So it's very large. Okay. And it has a large robotic arm on it that had the sample collection mechanism at the end. So it's one of the important things about the mission is we don't actually land on the surface and do operations on the surface of Bennu. We touch the surface kind of like you would if you were bouncing on a pogo stick. So we stick out the robotic arm on the spacecraft, has the sample collection head at the end, and we slowly descended to the surface and basically bounced off like a pogo stick, and then fired our thrusters and backed away. And that contact of just 10 to 15 seconds was enough to collect the sample.
Okay. Yeah. A very interesting design. Now, Nicole, I'm going to go to you for the actual kind of sample collection thing. But for that, you did mention OSIRIS-REx sort of orbited Bennu for a while to track its trajectory. What was it measuring? Was it just taking calculations of mostly navigation, or was there some element of composition that could help in determining its trajectory? What was the important measurements there?
Well, from a navigation perspective, we had to when we first arrived at Bennu, we had to learn what Bennu's characteristics were, its shape and its mass more precisely.
Okay.
And so the first kind of orbits we flew by and flybys were just to kind of get to know Bennu, sense its gravity a little bit better, and start to develop a model that we would use for navigation. And so the first few phases of the mission were really focused on that. We got a lot of good scientific data too, but it was about refining our ability to navigate. Then we got in close. We got into orbit. We started doing detailed flybys using that better navigational knowledge that we got. And that's where we collected the detailed maps. We flew by to all kinds of different geometries, looking at Bennu with different solar illumination and thermal conditions, and built up these maps. And the point of doing that was to understand the surface well enough to know where could you go down and collect a sample, where were the good sample sites, where would they have sampleable material. But it also provides this vast volume of scientific analysis, and there were all the science teams that were off studying those observations and learning as much as we could about the composition of Bennu just from the observations.
I'm thinking about all that work to find just the right spot. And Nicole, I'm thinking about it from a curation perspective, and particularly the design of what was going to be grabbing this sample, because from your perspective, right, one of the first things you mentioned in terms of comparing with Antarctic meteorites is that they're sort of like, I don't know if contaminated is the right word, but they're not pristine in nature. And one of the interesting things about Bennu is its pristine preservation of some of the earliest interesting parts of the universe. But what do you need to design in terms of the capsule, the hardware that actually keeps that pristine in space for a long time, through the atmosphere into Earth's atmosphere, right? There has to be very specific scientific requirements to make sure there's not, I don't know, an introduction of air or something. So what went into the design of making sure that this sample was truly pristine?
So, and it does interface with, I'll call out to everybody who was involved because it was before I was involved in the mission, but the sample was collected with pure nitrogen gas. So Earth's atmosphere that we breathe is 80% nitrogen. It's the other 20% that we really have to worry about, oxygen and humidity and carbon dioxide altering the sample. So by collecting it with pure nitrogen gas, which then when the sample ultimately comes to Johnson Space Center, we will be storing it also in a pure nitrogen environment. And that really gives us a lot of way to preserve it upon collection. Then sealed inside the canister, there is a filter so when this sample return capsule comes through Earth's atmosphere, that filter will protect the sample from humidity. And there's a very tortuous path that oxygen can get to it, but if we get the sample as quickly as we hope to, and we're working with our colleagues in recovery at Lockheed Martin, that we'll collect the sample as quickly as possible and actually connect it basically to a nitrogen bottle here in Utah to maintain that nitrogen atmosphere and keep it from having any of the contact with Earth's atmosphere that just always happens to meteorites, no matter how rapidly you collect them.
Okay. All right. So that's interesting.
Like Nicole, you're alluding to the fact that there was a huge amount of work that was done just to keep the sample pristine.
Yeah.
And that went all the way back to when the spacecraft was being developed to make sure we weren't using like tapes that would have adhesives that could be mistaken for organic materials in the sample. So there's been this huge effort to keep all of the hardware that makes up the sample return capsule pristine. And then Nicole is talking about all the ways that in the processing of it, we're trying to make sure that there aren't any contaminants that are introduced. And the other thing I think it's worth mentioning is the sample is going to be very unique because of all the characteristics you talked about. It's very unique from the existing meteorite collection. So we can go and collect these meteorites in Antarctica, but a lot of the material that we think we collected at Bennu is not generally the kind of thing that would survive entry through the atmosphere without being in this protective aeroshell enclosure. So that makes the very unique nature of the sample.
And I know, you mentioned just the amount of planning ahead of time to think about stuff like that. But I know even with all your down select to actually pick Bennu and make that mission profile what it was challenging to get there. You mentioned Bennu is small in size, and that comes with navigation challenges. Mike, what were some of those challenges when by the time you launch, you're heading to the asteroid, but the challenges of actually sort of getting there and navigating the spacecraft the way that you want to?
Yeah, well, this is something I really like to talk about because my background is as a navigator.
Yeah.
And I worked earlier in my career, like developing GPS receivers that could be used in new regions in space. So when we got to the challenge of trying to figure out how to do this mission, we were really doing a bunch of things that were pushing the envelope for deep space navigation. To give you an idea, Bennu is only 500 meters in diameter, so the gravity is very small. When we model spacecraft orbits, we also have to model things like the solar radiation pressure from the sun. So pushing the photons hitting the spacecraft are creating small accelerations. Normally, these are really small forces, but at Bennu, the force from gravity is almost the same as solar radiation pressure. So when we're orbiting Bennu, we're kind of doing this dance between, to balance out these small forces and achieve the trajectories we wanted. What that meant is little perturbations that come from the spacecraft can really push the spacecraft around. So like if the thrusters fired, change the attitude, and it's not balanced, that can be a large perturbation. Heating and cooling of the spacecraft surfaces are accelerations we were able to see in the data. We could see as the spacecraft slewed and surfaces heated and cooled, it would get small accelerations that would change the orbit of the spacecraft. So our navigation team had to develop all these really high fidelity models to be able to predict this behavior. And that was needed because when we're doing these orbits, we have to know where to point the cameras to observe Bennu. And you have to predict that ahead 1 to 2 to 3 days in the future to be able to plan those observations. And so there was this cycle of having to update the navigation and have the science plans fall along with those updates to be able to capture the images and the science data of Bennu. So it was really great. And we had just an amazing navigation team of people kind of rising to the challenge to solve some of these problems and make the mission work. And it really did work. We really achieved, all the things we weren't sure we were going to be able to do before we arrived, in general, worked much better than we thought we would and really just enabled the mission to be a great success.
Delicate was the word that was coming to mind for me. It's like you have all of these forces on top of gravity and just a little, like you were saying, just something else, a little bit of heat, a little bit of solar radiation becomes such a large factor. And as you were saying, it seemed like it was kind of like a rapid response team, the navigation team, right? Because you put in your models, you put in what you thought the spacecraft was going to do, you looked at the data, see what it was actually doing, and then was it as kind of rapid as I'm anticipating, where you see some change and like, all right, we got to go change that, because we have to think about, as you're saying, when the instruments are facing Bennu. Was it as rapid as I'm anticipating?
It really was kind of a rapid cadence.
Cool.
Because what we had to do was we had this cycle of before a science observation or before a maneuver, we would record images, optical navigation images, downlink them to the ground through the Deep Space Network, process the revision to the trajectory based on that data, and then upload a new trajectory, and that would guide the new pointing to the observations. So this whole cycle took about 24 hours. It required Deep Space Network passes 2 days in a row to work, one to get your OpNav images down, one to send the trajectory up. And so that process had to be repeated something like 150 times over the course of the mission to do all of the navigation and observations over the mission. So it was, people had to work and meet their deadlines in order to get that process closed in a 24-hour time frame. Later on, when we got to TAG, we actually were able to incorporate some autonomy, where the spacecraft had to do some of this navigation techniques on its own. But for a majority of the mission, we had to have the ground in the loop to do this. And so it was a highly orchestrated process.
Fascinating. And I know the story of, it's the story of when it actually reached Bennu and the story of the sample collection is fascinating in and of itself, because it was full of surprises, right? There was stuff about this is the interesting thing about science and exploration is you have a lot of models, you have a lot of ways of predicting what's going to happen, and then you actually do it, and it's surprising. What were some of the bigger surprises and curveballs of this mission?
Well, the biggest one was in December of 2018 when we saw the first resolved pictures of Bennu, and we realized it was just incredibly covered in rocks. So we thought, based on our observations of similar asteroids, that there would be these kind of large areas or kind of like sandy beaches with lots of fine-grained material, and we would be able to easily navigate down to the surface and pick this up up with our sample collection mechanism. When we got there, there was no place like that on Bennu. And to give you kind of an idea, we designed the spacecraft to be able to land with an accuracy of about 50 meters. So if you drew a circle on the surface that was 50 meters in diameter, we would be able to land somewhere in there using the navigation techniques that we had. The best tag site that we found after we did the map of Bennu was about 8 meters in diameter instead of 50. And this really just meant we would have to use a totally different approach for the navigation.
You needed a bullseye.
We started, and that was what we call it. We called it bullseye tag initially. How are we going to do the bullseye tag? So, some of the changes we made were to basically abandon. We had this really kind of simple LiDAR-based technique for measuring a light range to the surface, using that to update the navigation. We had to shift and adopt an optical navigation, vision processing-based technique to do the navigation that was much more precise. So this was a whole development that we undertook after we arrived at Bennu to change the flight software in the spacecraft to do this new method. So it was really kind of an exciting push-up. And that was just one of the surprises we ran into. So.
Yeah, the one that comes to mind for me is the actual composition of the asteroid itself. You would think like it's just a floating rock, like a solid, hard rock, but that really wasn't the case.
Yeah, it's really a rubble pile, right? and the density of the material on the surface is really, really low. So
it's kind of like, what was the analogy you used? It was like a ball pit was...
Yeah, so when we actually did the tag and we touched the surface, I mean, that was one of the biggest uncertainties we had, is how would Bennu respond when we touched the surface. And all of the assumptions we had, we were way on the far end of the spectrum, that the surface exerted almost zero pressure against the spacecraft when it touched the surface. In fact, we had an accelerometer trigger for firing the gas bottle that collects the sample, and we just barely hit that threshold. The acceleration was so small. We basically understand now that if we had not, the spacecraft touched the surface, fired this gas bottle, and then a few seconds later fired its thrusters to back away. Mm-hmm. If we hadn't fired the thrusters, the spacecraft would have just kept descending into the surface. It, just like it was landing in a ball pit that you would play in at the mall or something. But so what we took away from that, the scientific result, is that the surface has very, very low cohesion. I'll think of almost these styrofoam popcorn or something like that. And as we touched the surface and pushed into that, there was no resistance. And then when we fired the gas ball, we excavated this huge crater about 0.5 meter deep and perhaps 8 meters in the long axis. Tons of material that was moved by just this little gas bottle we fired to collect the sample.
Wow.
So that's very exciting. There's a lot of other cool scientific results that the scientists were able to extract from the insights that we got when we touched the surface.
Yeah, I'm thinking about the sample collection, Nicole, and this Mike's talking about this gas pressurization, right? And it sounds like you fire some gas to get the samples that you want. So what is it exactly that the scientific community was looking for? What is the sample? What's inside the return capsule now? And how did that gas technique work?
So the gas was to entrain the sample into the sampler head, which is a little over 1 foot in diameter, just to give you a sense of the scales Mike's talking about versus the areas they had to work with and the challenge they really got. And I also just want to take an opportunity to step back. And one of the things that's really powerful about spacecraft exploration of asteroids is we see these kinds of things, right? This kind of texture, this rubble pile, the cohesion, we really can't get that from telescopic observations or from studying the meteorites on Earth because, as Mike highlighted earlier, the meteorites that we have on the surface of Earth are things that could survive passage through the Earth's atmosphere. So they already have a fair amount of cohesion, not to fall apart and just melt into small pieces that are very difficult to recognize to make it to the Earth and have an actual rock that's still an asteroid rock. But in getting, the scientists wanted to have what Bennu was, though they recognized, the asteroid operations recognized at least 2 main lithologies and a lot of smaller lithologies that was observable in Bennu. And so we're hoping we'll at least get those 2 main lithologies, and we might get some other, so we might get a bunch of different types of rocks that have different histories, and that will be able to tell us a lot more about Bennu's formation and the larger asteroids that it probably came from, But those are the kinds of things that we need the tools that we have on Earth. Big labs, large pieces of equipment that you can't really fly on a spacecraft, and the diversity of all the different types of instruments that we have on Earth. And that's one of the really powerful things about a sample return mission.
Yeah, and I definitely want to dive into that a little bit more when we talk about what happens next. But just really quickly, just for my own knowledge, lithology. You said what is?
Oh,
that?
so it's a word for. So litho is rock, so it's different types of rocks.
Different types of rocks, okay.
Yeah,
Okay.
so it's the two main ones are, we think, carbonaceous chondrite-like, though they may not be like any carbonaceous chondrites we have on Earth. We'll see when we actually get to study them more closely.
Okay.
And then some of the other ones actually seem like they're parts of different types of asteroids, non-carbonaceous chondrite-like asteroids.
Okay. And you're just fingers crossed you have both?
I mean, fingers crossed. I mean, the pictosite, that's a good candidate.
So it's very likely that you have both. Okay. All right. There was one more interesting thing that you that was like a surprise was these little, I think it was like particles that are coming off of Bennu. What was that about?
Yeah, so one of the other just total blindsided us very early in the mission, just as we were getting ready to insert into orbit around Bennu, we noticed in the optical navigation images, we look for stars in those images. We take long exposures so we can see stars and use those to help orient the cameras for the navigation solution. We saw a lot of points of light in the images that were not stars. We even saw some streaking in the images. And so upon closer analysis, we realized that Bennu was basically having these events that ejected little bits of material into space. So I told you already that the material is very loosely held together on the surface, right? So we believe that it could be micrometeor impacts or thermal effects of thermal fracturing of material, but there were events that were happening, every few days that would cause just like sprays of particles ejected from Bennu that we were able to observe with the spacecraft. So these are things that are just a few centimeters in size that were leaving the surface of Bennu. Some were entering into orbits around Bennu for a few days and then landing on the surface again. And so using these images that we took for OpNav, we made this amazing scientific discovery about Bennu that has never been observed before. But it was also in part because we were so close to Bennu and it was so small that we were close enough to see these things, because you can only see particles that are a couple centimeters across if you're a couple kilometers away, which is what we were. So there was just a really great synergy there between the engineering that took to fly the mission and enabled us to have this scientific discovery that was a big surprise.
Wow. Absolutely fascinating. I've never gone into this much detail about just OSIRIS-REx and the mission and being there. It just sounds like a thrill. It was just a very exciting mission. But, I think part of the reason we're here today is because it's coming back, and that's a big thrill as well, particularly for the scientific community. And Mike, you said you're mentioned here because you're here at the Johnson Space Center because the planning is really picking up. A lot of people are getting really excited about the sample return. You guys want to make sure all your ducks are in a row. Nicole, I want to head to you for a second because in terms of planning, I think one of the thing that really jumps out at me for planning for OSIRIS-REx's return is all the facilities and the process of actually getting that sample to a facility, how you're going to house it, how you make sure you have the right nitrogen and everything like that. So what are you doing on the curation side to make sure that everything's in tip-top shape for when that super precious sample comes back?
So right now, and what we've been working on actually for the last couple of years, is really being ready to make sure we first and foremost can protect the whole sample in our lab at Johnson Space Center. So a new lab was built, construction started on it in 2020 and finished in 2021. We've been monitoring the lab since then, and also all of the equipment that we're putting in the lab. We'll have specialized glove boxes that are specifically for handling the OSIRIS-REx sample and for taking apart actually the parts of the sample return capsule that we'll bring to Johnson Space Center immediately, the sample canister and that tag SAM head, the collector that the sample was actually collected. We'll take that apart inside of a glove box because that's the way we can protect it from Earth's atmosphere. That glove box will have only a pure, dry nitrogen atmosphere. And then people working with their hands through very heavy rubber-ish gloves that are all contamination monitored. We get the same thing that Mike mentioned on the spacecraft side. We worry about all that same contamination contamination stuff on our side, carefully vet everything that's going to go in that lab. Everything that might have contact with the sample will go through a thorough cleaning, autoclaving, and or baking out to remove organics, just like what happened with all of the spacecraft parts, to make sure that all of that work to protect the precision of the sample continues to pay off by us, preserving it in the lab. And then it will end up going to a bunch of scientists all over the world, and some of it will depend on what they need to do. There are scientists that absolutely need it to be maintained in a nitrogen atmosphere. There are others that the work they're doing doesn't necessarily need that as much. So it will really a case by case. And there's things that we'll actually be doing within our on-site at JSC, where we have a specialized sealed container. We'll take it, for instance, to XCT scanner and CT it in a sealed container, so it never leaves that dry nitrogen curation environment while that analysis has taken place. So that's also what we've been working on, is containers that we can do that stuff in, that both work with the instrumentation so you can still take the measurement, but also that protect the sample.
Do you feel at this point that from a curation perspective, you guys are armed and ready for the return, or you still have a couple of things?
We are in a good position, but we still have things we're working on. There's still, there's still things that our lab has some stuff in it, but we have a lot of equipment that's going to be coming in the next couple of months. Those glove boxes are one of them, which is a big thing.
Yeah.
So we've been working really hard in the last couple of years to get all that stuff here. And right now it's starting to show up and be ready and go through all the cleaning we have to do to be ready. So it is still a busy time.
I bet, yeah. Is it your role that is also overseeing the research proposals and thinking about and making selections and how you're going to transport them to different researchers? Or
so we have a role in it, but we're not the only decision factor. So for the science team, there's an intricate plan of analyses and that to answer certain hypotheses, and then we'll interface with the science team to make sure that we can get them the samples we need. We always have, in curation, have this tension of we want to make sure we preserve some material for the future when there may be new instruments, things that can do stuff we can't imagine now. But we also brought back this sample for it to be studied by scientists.
Right.
And some of the ways you can study it requires it to be destroyed, requires small parts of it to be exposed to Earth's atmosphere before it gets destroyed, or just to do the measurement. And so having that balance, we will be working with the science team so they can address their hypotheses, but also, as for instance, if we have two lithologies, we'll try to make sure that we're preserving some of each lithology for the future. And so that will be the balance of letting their scientific questions have already been thoroughly vetted. This mission is a science-focused mission. That was how it was selected by NASA. And then later on, we will have broader scientists who aren't part of the science team be able to propose research they want to do, and that will be peer-reviewed by a board of other scientists, which we will convene. So we'll select people with different interests, but they won't be people who are NASA people. There will be some independence to review that science, but we'll be part of that.
Yeah, and I want to add to what you're saying, Nicole, that the Dante Loretta, who's the principal investigator for the mission at the University of Arizona, he's leading this whole sample analysis team and making the plans for the scientific investigations and prioritizing all of those. And the curation team is really supporting the science team in that role. But you mentioned that part of this sample will be archived. That's a really important point. All of this entire sample analysis plan only uses 25% of the sample. The other 75% is planned to be archived for future generations. So our grandkids would have access to write a proposal to examine part of the sample with a new scientific instrument that wasn't available today. And that's the same philosophy that the Apollo samples have been curated under.
Yeah.
So.
And we've seen the benefit of that very recently, too. I know you're probably more intimately familiar with the ANCSA efforts. This was Apollo samples that were preserved for pretty much 50 years, right? And opened very recently because exactly what you're saying. The technology improves so much that we can do new, fantastic research, and it's thanks to the 50 years worth of preservation that we're actually able to do that. But it's like that logic, pretty much, right? Yeah.
Exactly. And the Apollo curation folks, they're in the same building as me, just down the hall. We talk to each other all the time. We're always learning lessons from them.
Yeah.
And so the ANCSA stuff really came to fruition 50 years. And we are planning to have a similar sample, a hermetically sealed sample for OSIRIS-REx that will be kind of analogous to that. But also within the 50 years since Apollo, there's stuff that has been happening just in the last 10 to 15 to 20 years that couldn't have happened 50 years ago. And so that was allocations from the regular collection. And we'll be doing that as well for OREX. So that's one of the things I look forward to for the decades of my career to come, being part of allocating sample to the community as the science around asteroids develops.
Fantastic. Yeah, lots of work ahead, lots of prep happening. Mike, in terms of other prep for the return, before we actually talk about the return itself, what else has to be coordinated on the ground to make sure teams are truly ready for when this thing comes and you guys can go full force into studying it?
Well, there's a lot. I mean, obviously, before the spacecraft launched, we had to go through and show that we had good plans for recovering the sample, but all of those plans were made in 2014 or earlier. And so we're dusting those off and figuring out, okay, well, we said we were going to do this. Does that still make sense? Is that the right answer? So there's a few different aspects. One is just the trajectory design and making sure that that's all in the place that it needs to be, and that we're, the plan for conducting the maneuvers on the spacecraft to get the sample home. There's a whole component of looking at the various things that could go wrong, and can we ensure that we can recover from those, or if there's a failure of the spacecraft, that there isn't a safety concern for anyone. And then there's all the preparations on the ground. So Lockheed Martin, our partner, has responsibility for executing the recovery operation with their personnel, but we're working very closely with our Air Force and Army colleagues. And so we've got to make all the preparations for how we will operate at their facility, contracting with helicopters, all that kind of stuff to make the plans and make sure we're ready to go this September. So
yeah, lots to go. Let's go into the return itself. So what is going to happen? OSIRIS-REx is on its way back. It's going to pass through the atmosphere and land somewhere. So what's the trajectory look like?
So we set up all of this in May of 2021 when we did a maneuver on the spacecraft that caused us to leave the vicinity of Bennu. And that set us up on this we basically do 2 orbits of the sun with the idea that the trajectory intersects the Earth in September of 2023. So right now the spacecraft is headed back towards the Earth, but it's slated to fly by the Earth. If we didn't do anything else, spacecraft would fly by the Earth at a distance of about 2,500 kilometers. So in July of this year now, July's coming up fast. July of this year, we're going to do another burn on the spacecraft and essentially walk that flyby distance closer. So the spacecraft's then targeted to fly by at about 250 kilometers. And that's intentional because if something goes wrong with the spacecraft between now and then, we don't want it to be on an impact trajectory with the Earth.
Makes sense.
But then about 2 weeks out, we're going to walk that trajectory towards the atmospheric interface point. So where does the capsule have to intersect the atmosphere to land in Utah? We're going to aim for that spot. And then the spacecraft will be aimed for that spot for about 2 weeks. And then 4 hours before entry, just the sample capsule is released. And then the spacecraft does a divert burn to miss the Earth. And so that sets up the whole return or the recovery of the capsule. Spacecraft enters the atmosphere. It takes about 2 minutes to go from off the coast of California, where it interfaces with the atmosphere, to the area close to Utah. There's a drogue chute that comes out to make sure the capsule's stable during the reentry, and then main parachutes come down. So about 13 minutes after it hits the atmosphere, it's going to be on the ground in Utah. And we'll be tracking it with optical and radar trackers, and we'll have an aircraft that is tracking the entry. All of that information will be used to calculate where we think it's going to come down in the ellipse, and we'll send our helicopter teams out to try and go get it.
Excellent. Now, the capsule that contains the sample is coming back. What happens? You said the other part of the spacecraft goes back into space. What happens with that one?
So originally, that's an interesting question. We could go a whole podcast on that. But the spacecraft was after it flies by the Earth, it gets a gravity assist by the Earth, and that actually pushes its orbit into the inner solar system, so down towards the distance of the Venus orbit around the sun, so about half the distance between the Earth and the sun. That's a lot hotter regime than the spacecraft was designed to operate in, and so the original thought was, well, the mission's just going to end then. We'll decommission the spacecraft. It's not going to survive that perihelion passage. But the unique trajectory designer named Brian Sutter at Lockheed Martin came up with this really great mission concept that allows OSIRIS-REx to fly for several more years, several Earth flybys, and rendezvous with another near-Earth asteroid called Apophis in 2029. And so that flyby we do of the Earth is the first maneuver that sets up that arrival with Apophis in 2029. And so we've come up with design and configuration of the spacecraft to try to protect it during that hot environment. And we think that we've got a chance to survive and a rendezvous with another whole mission and characterize it in great detail.
Yeah, with all the same instruments that were used for Bennu.
Exactly.
Wow, fantastic.
So that's a story for another day. But the team is going to be trying to keep the spacecraft going, and it's got a lot of fuel in the tank, and all the instruments are fully capable. So we're excited about doing even more with it after the sample gets home.
You think you're free in January 2029? We'll get you on the calendar now. What
All right,
week works for you in 29?
Yeah.
We'll find a day, maybe later. Okay, fantastic. Now, the capsule, let's go back to the capsule that lands in Utah. The recovery operations, Nicole, I'll leave to you. You mentioned something where like someone runs over with like a nitrogen canister to keep the sample pristine. But what else? What is all part of the recovery operations to really grab this thing?
Yeah, so first we do have to, our field recovery team will do have to do some safety assessments, safety first always. And then the capsule will be brought back via helicopter actually to a portable clean room we'll have set up. And there's a few disassembly steps that have to happen before we can run over with that nitrogen bottle.
Okay.
The curation folks are eager for that to happen, but
Yeah.
for safety and just to access the septum where we connect in the nitrogen, the heat shield and the back shell actually come off in that portable clean room that we're setting up. Same kind of contamination controls requirements the spacecraft had and our clean rooms at JSC had of really limiting what that sample return capsule might be exposed to in the clean room as these disassembly steps take place. And then the sample return capsule, it's kind of like a Matryoshka doll a little bit. There's next a sample canister inside of it, and inside of that the tag SAM head is there. So basically the back heat shield and back shell come off. We'll have that sample canister. That's where the nitrogen purge gets hooked on. It'll be put in a shipping container and then flown to Ellington Field down here in Houston. And from Ellington, we'll bring it to JSC to get it into our clean lab. And then we'll do the rest of the disassembly of the canister inside a nitrogen glove box.
Okay. This pop-up tent is also in Utah?
Yes, it will also be in Utah.
Okay. That makes sense. So the flight is relatively short. You can do that, and then once everything is prepped, then you can take that long journey back to Houston.
Yeah, we want to get it on that nitrogen purge as soon as possible. There was a requirement, or a goal of 2 hours, I think, to try to get the capsule out of the field and into the clean room on the purge.
Okay. All right.
So the canister has the filter part, so the sample is still more protected than a meteorite would be during that 2 hours, but we still want to get it on the nitrogen purge as quickly as possible.
I bet. Now, once it arrives at the Johnson Space Center and the curation facility, what's about the time frame you think to do everything you want to do? Make sure that you were talking about the facilities you have to make sure the sample is pristine, to divide it into the different boxes or whatever that were required for each of the researchers. About how long from the time it arrives at Houston to the time the researchers can really get their hands on it?
So it will probably take us, before we're actually shipping it out to people like Dante Loretta, the PI of the science mission, it will probably take us about a month because we are going to actually do a lot of spacecraft disassembly in those glove boxes. And we'll do some initial sample characterization. So to decide which samples we should send to the researchers, we need to know a little bit about that. And the science team is working with us in that. So they're going to try to do some imaging that is similar to what the spacecraft did on the asteroid to try to pick out, for instance, those two lithologies we mentioned before we even take any sample out of the glove boxes or even put it in sealed containers. And so we'll be working with them to do that initial description of the sample once we get it out.
My first thought is that is quick. A month. That is not a lot of time from the time you get it, characterize all these samples. I'm sure you're going to be communicating with the researchers because they're going to want to know what they're getting, right? Basically like a profile of here's the sample you're getting. That's pretty quick.
I mean, there'll be more for them to add, and we are going to also do something we're planning to do something called a quick look sample. So in one of the very earliest stages of disassembly in the glove box, so we'll take the lid off the canister. We won't even have gotten into the tag SAM, and we're planning to try to brush some dust off the top of the tag SAM, which we think will be there. Something we haven't talked about really yet, Mike, on this is the tag SAM, the collection, touch and go collection event was so successful that the sample collector was overflowing with sample before it was stowed in the sample return capsule. So we do have the expectation that there will be some dust on the hardware other places, and that makes that purge more important for protecting all the sample. It's great to have more sample than we were expecting, we think. But we are also expecting to have this additional sample within the canister. And so that will actually go within Johnson Space Center. It will start being analyzed so we can get some early science results, both to share with the scientists who are anticipating getting the sample early on as part of the science team, but also to share with the world so we can start to tell what we brought back.
Yeah, I mean, I should mention too that we're planning to allow the public to try to follow along in this process. NASA's planning on making the actual landing of the SRC a big communications event, so it'll be covered live.
Fantastic.
And then the sample will transport to Houston as early as the next day. And some of those initial steps of opening up the sample canister and seeing the sample material for the first time could be in that first day or two. So we were hoping, to make video and other things available of that process and through a blog and other social media sources and stuff like that. So the public's really going to be able to follow along and see the wow moments of looking at the sample for the first time along with the team. So.
Yeah, I think there's a lot of people in the public that they may not be doing the research, but I think they're excited about the possibilities. This is answering some big questions here. I was just imagining, Nicole, as you were describing that process of disassembling the spacecraft, like it's almost like you're cleaning off the spacecraft, but you're not throwing any of that dust away.
No, we're not throwing any of it away. We're going to try to keep
preserving all of
Yeah.
it. That's so fun.
For sure.
But yeah, I mean, really, the reason we're talking about this and everything all of the effort really that's going into this mission, right? We talked about all the challenges and we're trying to make the most even of the spacecraft. The spacecraft is not done after this mission. It's going to go to another asteroid. There's just these fantastic questions. And I can only imagine what the scientific community is talking about, is thinking for this sample return. This is, I mean, do you have like a vibe on what the scientific community is saying about what they're thinking for September and what that's going to be like?
Well, I can talk about they've broken it into 4 key questions that the science team is trying to address through the analysis of the sample. How does the sample compare with observations that the spacecraft made at Bennu in terms of, with the interpretation we've made of what Bennu's composition is? Does it jive with that? How does the sample contain organic compounds that could have influenced the origin of life, what Nicole was talking about earlier? What does it tell us about the early history of the solar system and the formation of the solar system? And then also, has it changed since we collected it? And that could be the, clumps of material that broke up or not, and characteristics about the actual material that we collected. So those are 4 key questions. There's something like 38 institutions all over the world that are going to receive elements of the sample. 180 something team members on the sample analysis team. And I should mention, too, that we have 2 international partners with the mission. The Canadian government contributed one of the instruments on the spacecraft and in return gets a portion of the sample to study however they want. And Japan is a partner, too. The 2 countries made an agreement to exchange samples between the OSIRIS-REx program and the Hayabusa 2 program that would give both sample teams the chance to analyze something in the event that one of the missions failed. So they've both been successful. So those sample teams, in some cases, are analyzing samples from 2 different asteroids.
Yeah, too much to go around.
Really
That's
exciting.
great.
So
awesome. Are you hearing the same thing from your end, Nicole? The just general excitement and
Absolutely.
Yeah.
I think a lot of people are really excited to both the science team to answer the questions that Mike highlighted and to get a sample of an asteroid that we know exactly where it came from. We know what this asteroid looked like, the geologic context of it being a rubble pile, all of that additional information that we don't usually have if you're studying a meteorite. And getting into, we haven't talked about too much, but that most of the samples in our asteroid belt are left over from the earliest formation days of our solar system before the planets were built. And so having that unmodified, really pristine material does get into all these early solar system questions of the organic compounds. Building blocks of life is really a big one, but lots of others too, of water in the solar system and other features that we're expecting to be able to explore and have the scientific community explore for both the initial sample analysis of the science team and many, many years beyond.
it's like a rewrite the science books level of information that we might get from this. It's very exciting. I mean, so Mike, I'm sure you're excited because you've you've dedicated a lot of your career to this mission. You've sort of, I guess, moved up the ladder in terms of responsibility and what you're overseeing. It sounds like even your plans after it returns is to continue in a different role with this mission. It's almost like you have like a giant fingerprint on this. Like your career is like really has a large fingerprint of that is the OSIRIS-REx mission. How does it feel really to contribute to something of that magnitude?
Well, it is amazing. It's one of the things that's kind of amazing is that it's already 2023 and we're just months away from the sample coming home, because I can tell you that in 2013 or 2014, that seemed like a lifetime away. So it's kind of hard to believe that some of us have been involved with the mission for so long. And just looking back at all the challenges that the team overcome, it really gives a great sense of pride, not just for whatever you contributed individually, but being part of such a great group of people that rose to the challenge and really worked together in the way that only great groups do. So that's what I'm really most proud of is how the team worked together and the memories that they have of making this a great success. In terms of what I'm going to do after, though, I think I should talk to Nicole about going to Antarctica and looking for meteorites, because she did it before the mission. Maybe I'll do it after.
You should.
Check Antarctica off my list,
That does sound very exciting. How about Nicole, you mentioned your passion for OSIRIS-REx early on and eventually making your way to being a significant part of this mission. In a sense, you're there. You've made it. You've done it. Do you feel that level of connection with the mission?
Absolutely. So I mentioned before I came on in 2020, but I watched the launch on my cell phone with a friend. I followed the Rendezvous NASA Live program as the spacecraft got to Bennu. So it is really amazing for me to be part of it, especially, I fell in love with asteroids through meteorites, but I also being able to be part of a mission exploring them and to be able to be part of the group that's going to take care of this sample long term, that this is going to be its new home at Johnson Space Center, and I'm going to be part of the team that gets to work with it and help scientists study it is really cool.
All right. Well, I hope you let me know first if you find anything like super interesting, and then we'll bring you back on to the podcast. I'm very excited. This is very cool to have you both here to talk about it now, but really, I can't even wait for September. I'm sure you guys are anticipating it as well, but September is going to be pretty big. So wishing you both the best of luck. There's a lot. It sounds like on both of your sides, there's still a lot to do up to September.
For sure.
So yeah, definitely appreciate your time, especially today. I'm sure it's even busy now, but thanks for coming on, talking about OSIRIS-REx, getting folks excited about this mission, and best of luck to both of the teams for getting ready for September.
Awesome. Thank you.
Thank you.
Houston, go ahead.
Dock of the space shuttle.
Roger, 0J, and I feel fine.
Shuttle has cleared the tower.
Became a stage for all mankind.
It's actually a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Never Houston, welcome to space.
Hey, thanks for sticking around. Really enjoyed the conversation today with Mike and Nicole. I hope you learned something today. This is, of course, not the first time that we've discussed OSIRIS-REx. It's a really fascinating mission. You can go all the way back and listen to episode 27, The Search for Life, when we recorded it before OREX even reached Bennu. And then you can go forward and listen to episode 253. We did this one a little bit more recently. It's called The Blueprint of Life. That goes into more detail about a novel kind of research that may be used on OREX's samples. You can check nasa.gov for the latest at any time. Go to nasa.gov/podcast to find us and many other NASA podcasts we have here at the agency. And of course, if you want to talk to us, you can find us on social media. We're on the NASA Johnson Space Center pages of Facebook, Twitter, and Instagram. And on those pages, you can use the hashtag AskNASA to submit an idea for the show. Just make sure to mention it's for us at Houston. We have a podcast. This episode was recorded on January 10th, 2023. Thanks to Will Flato, Pat Ryan, Heidi Lavelle, Belinda Polito, Jaden Jennings, and Nila Ranji. And of course, thanks again to Mike and Nicole for taking the time to come on the show. Give us a rating and feedback on whatever platform you're listening to us on, and tell us what you think of our podcast. We'll be back next week. Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 284, The Student-Built Camera Mount. I'm Gary Jordan. I'll be your host today. On this podcast, we bring in the experts, scientists, engineers, astronauts, all to let you know what's going on in the world of human spaceflight and more. NASA loves working with students. Heck, that's how I got a job at NASA, was starting off as a student. But there are certain programs that allow students to work with NASA in a different way than what I'll call your quote-unquote standard internship opportunity. I'm talking about a program that allows students in high school to design and build hardware that flies to the International Space Station and is used by astronauts. On this episode, we're going to be talking about HUNCH, which is, of course, an acronym that stands for High School Students United with NASA to Create Hardware. We've discussed the overall program on this podcast before, episode 106, if you're interested in going back. But don't worry, we'll briefly review the program on this episode. But today is focused on a specific student experiment that recently flew to the International Space Station aboard the SpaceX CRS-27 cargo mission. Astronauts have been looking for a tool that would make taking beautiful photographs of Earth a lot easier. So students took on the challenge, from design to construction and testing. On this episode, we have Flight Configuration Project Manager Mike Bennett, Design and Prototype Manager Glenn Johnson, and from the student team who actually designed and built the hardware, we have Shane Johnson. All right, let's learn about this student-built camera mount. Enjoy.
T-minus 5 seconds and counting. Mark. Mission start. Launch commit lights are correct. There she goes.
Houston, we have a podcast.
Mike, Glenn, and Shane, thank you so much for coming on Houston. We have a podcast today.
Thank you for the opportunity. Thank you.
Thanks a lot. I really appreciate being here.
Super excited to be here. Thank you.
All right. Now we have Mike and Glenn here in the studio. Shane, you're calling to us from your dorm room. Congratulations. We're going to be talking about a high school program, but you're in college, right?
That's correct. Yeah, I'm a first year.
All right. Well, congratulations. So I'm glad to have you on. I'm glad you could take the time to talk about this experiment because this is really cool. I wanted to go around the room and get other listeners familiar with your voices. Let's talk about your role. Let's talk about just sort of what HUNCH is, kind of set a foundation for our listenership. Mike, why don't we start with you?
Okay. My role is Flight Configuration Manager. I work with the high school students once a project has been identified to move on for development to flight. I work with them in their drawings and their material selections, and they're all high school students, which is the cool part of this.
That's great. How did you get this role? What are you an educator? Do you have a background in education or anything like that?
I have a background in education.
Okay.
I was in it for 30 plus years.
Oh, fantastic.
And I was also a part of the HUNCH program for over 15 years when I joined. I came over into the HUNCH program itself. So I had students for over 15 years that were building training and designing flight hardware. And then I had an opportunity to join the team and be on this part of it.
All right. Well, I'm super glad to have you. This sounds like something you're very passionate about, is working with students.
Absolutely.
All right. Glenn, a little bit about your background.
So I came into the program about 7 years ago. I'm the manager of the design and prototype. And so my job is to find and come up with projects that NASA needs. So I work with engineers and astronauts at different occasions to find things for students to work on. And then I hand those projects out to students, and they start giving us prototypes so that we can find the best ideas, kind of mix them together, and then I hand it off to Mike and some of his team, and we turn it into the flight hardware that can make it to the space station.
So do you have more of a technical or engineering background, or are you also an educator?
So my degree's in physics. I was a high school physics teacher for a few years.
Wonderful.
Then I came to NASA after several years, and I was a trainer in crew systems. So I helped train the astronauts on the inside equipment for the space station. And after doing that for several years, I came into the HUNCH program as the design and prototyping.
All right. Well, it's great to have you too, and I know you have a lot of history on the beginnings of this particular experiment, so we'll definitely go into that. But Shane, I wanted to know about your background. Right, you went to high school, now you're in college. What's your story?
Yeah, absolutely. So in terms of Hunch, I guess I'll start from the beginning. I'll never forget the scene. It was the very first day of high school, freshman year, and I walked into my engineering classroom, of which Mr. Bennett, Mike, was also my teacher before he joined Hunch. And he took me around the classroom and showed me all the posters of different hardware that high school students from my school have sent up into space. And I remember that day I made a goal and that I was going to have something I made on the ISS. And so here we are, and we'll get to talk about that in a little bit. But yeah, so I joined the Hunch program my junior year, worked directly with Mike and Glenn throughout my junior and senior year, so I know them very well. And now I'm a freshman studying mechanical engineering at the University of Texas at Austin, Hook'em Horns.
All right. And I am going to go off on a limb here and say you are pursuing mechanical engineering because of your work on Hunch.
Definitely a factor. Yeah, 100%.
Right.
I'm also very big into like automotive and cars and that sort of thing. But yeah, definitely Hunch is a huge influence in my life.
Awesome. Mike, you must have given one heck of a speech for him to be like, this is my goal so early in high school.
It wasn't hard to get him enthusiastic. He was enthusiastic as soon as he walked in the door and saw what he could do and what we had the opportunities to do through Hunch.
That's awesome. Okay, well, Mike, let's go back to you for a second, and because we keep talking about Hunch, we keep saying this name. But for our listenership, just give kind of a brief overview of what is this program? What is it that we're talking about today?
Well, it's high school students united with NASA to create hardware. Through its evolution, we've gone through training hardware. We've gone to flight hardware now. We're also into culinary. We're into soft goods, and we even have video challenges for the students to do. And this is countrywide. This is around the entire nation. And so we've got schools, again, from the West Coast to the East Coast, and we have mentors that help and these tremendous students.
So it has a nice benefit of getting students hands-on opportunity, almost like a way to learn about actually designing and fabricating some hardware. But then we get the benefit, we meaning NASA, of actually getting to, we have an additional source of hardware. We have these challenges, we have problems that need to be solved, and we reach out to high school students to do it.
Absolutely.
All right.
Absolutely. It gives them a challenge, a thing that they didn't know they could do. They go in, well, I can't do that. I don't have the skills. And then they get their confidence and they see what they can do and what they can achieve. And that helps them throughout their career. And the hardest thing sometimes is convincing people that, yes, as a high school student, I actually did build this flight hardware or design this flight hardware. So, and it helps their career. It helps their career choices, their college choices too.
Yeah, that's one heck of a thing to put on a resume for a college application.
Right.
Is, by the way, I designed something in high school that flew to space. And I haven't even worked in the space industry yet. I don't have previous 5 years of experience or anything like that. No, they actually flew something. That's pretty cool. All right, Glenn, this project that we're going to be talking about today, it's a camera mount. Now, you mentioned you're the one that's interfacing with engineers, with astronauts. There must be some communication path that gets to, here's a problem that we need solved. And you come in and say, I think I know just the right people to do it. How does that process work?
Well, and on this particular one, I had a good friend, Bruce Blazine, has been somebody I've worked with for many years. He had been in the OSO team. Their job was to repair and keep the space station running all the time. And he had gone to a meeting one day and with the astronauts, and he said, Glenn, they've got this problem where they want to be able to put the camera in the middle of the module so that it's a better view of what's going on. And all of the hardware that we have right now puts it over to the side of the modules. So they can't see right down the center of the module and be able to display what's really happening. Do you think we could work on this? And so we sat around talking. Bruce had this original idea of what we call a ball clamp. And it allows a piece of hardware to attach to a handrail and then be able to swivel so that you can reposition things very easily. And so we started talking about how we could get kind of a long stick attached to this ball clamp and then put a camera shoe on it so that it would hold the cameras the way that we want. And so I went home later that night and I got myself a couple of pieces of aluminum tubing, square aluminum tubing, and I slid them together. And I put a couple of holes in there so we could have different positioning and things. And I took one of the ball clamps that we had printed up, and I attached it to one side. And then I don't think I had a camera shoe on the other side. And I walked it in and I said, "Hey, Bruce, what do you think of this?" And I happened to bring it along with me. And so it wasn't anything special about it other than just that we could represent the idea. And that's all we needed to do. And so I took it around to a couple of the astronauts and I said, "Hey, what do you think about this? You guys were asking for this thing." And I took it to Don Pettit and I took it to Paulo Nespoli. And I said, "Hey, what do you think?" And they said, "Well, yeah, that's kind of what we're looking for, but, it's kind of clunky." "Yeah, it is. Well, we need something that'll slide a little bit. Can you give me, instead of 1 every inch with a pip pin, can you give me something that's a little bit more slidey, a little bit more variable?" And after they told me that, I said, "Gosh, how come I'm not trying to use a monopod just straight off the shelf?" And that took a little while because if it's not sitting in front of you, you don't always think about it.
Right.
And so after I went over to a store and found one that would fit kind of our needs, and then we started saying, "Wow, wait a minute, if you want to set up a video camera or a camera in the middle, a lot of times you're talking to like a president of some country, or you're talking to some pretty high-end people, and you need a teleprompter because you've got a speech or a long talk." And so we started saying, "Hey, can we add like a piece of seat track?" And a piece of seat track is a way of how things on the space station are attached to either a handrail or mostly onto seat track. And it's kind of a long piece with buttons on it so you can place it in lots of locations. So we put a small piece of seat track on the side of it so that you could attach like an iPad or something like that and be able to read the teleprompter, use it as a teleprompter while you're working and talking on to this, whether it's the president or somebody else, and be able to kind of be consistent. But it also means that you could add lights to it. So we took a monopod, we put the swivel on the bottom, we put a camera shoe and a swivel on the top, and then we added some other pieces to make it so that it was a little bit more usable for their specific case. And then, it's easy to come up with ideas, but to make it ready for space, that's where I started running into trouble. And that was when Mike came in and started giving us, "Hey, well, how long do we really want each one of these pieces? What kind of materials do we want?" And so that really made a big difference.
Awesome. I'm glad you actually brought that piece of hardware for our listeners. That clinking and clanking was the thing that you fabricated at home, right?
Yeah. So it started off in my garage. And now to bring this back a little bit, the student portion is what's really important here.
Yeah.
So Bruce Blazine and I came up with these general ideas, but the problem is that we really need it to be, there's a lot of details in there. And that's where we brought our students in. So for example, the camera shoe, we didn't want to use a standard NASA camera shoe because it has like 20 parts and it costs a lot of time and machining to be able to put it all together. And so that's where I wanted to hand that off to Mike.
Yeah. Mike, take it from there. So you came almost kind of with a solution as Glenn was kind of troubleshooting some ideas.
Right, and that's a strength. We have such support from NASA mentors and all that to guide the students. And then we took it and we would take it and do prototyping. We'd make our models. We'd do our presentations back and forth. We'd get the invaluable feedback from all stakeholders and then just keep refining until we did get a very good and workable solution to it. And the students have the opportunity to work through that process that maybe they're not used to doing. And that gives them such a step up on doing that type of system.
So what's the process of Glenn comes to you with a problem? He says, all right, I think I have an idea of how I want this. How do you get that to students?
We actually have a roundtable meeting with the students, and we get which students may be involved, and I look at their skill levels, which will fit so they can be successful, and then we present the problem. We kind of identify where we want to go with it, and we just go through feedback, iterations on the design, and then constant communication back and forth until we get it. And quite a few 3D prints and things like that, and prototypes.
So is it Shane and a small team that you kind of pulled on, or was it, you mentioned Hunch kind of goes, coast to coast.
Right.
So how big was your army of students?
It really, counting the additive manufacturing, it goes all to the East Coast even on that. We have a school that does our 3D printing for Ultim, for Flight Ultim. Our design team was north of Houston and Conroe. That's right. And they did the design for the camera shoe. We did the ball clamp on the part of that. And Shane came in with an invaluable redesign on the thumb screw for it because we had
I didn't
feedback.
realize Shane's the one that did that.
Shane is the one. Sorry about that. Sorry about that, Shane.
That's funny.
It's all right. It's all right.
So he did an invaluable redesign so it was easier to tighten up the ball clamp.
Okay. All right, yeah. So Shane, talk about we'll go to you for a second because he's talking about there's a lot of different parts here. Mike comes to you with a problem. What was that like? The introduction of this design and how you went about solving it.
Absolutely, yeah. So obviously the first step is figuring out what the heck is going on, because I'd heard of like ball clamp and foot restraint and thumb screw and all these different things, but you have to place names to actual items because, like Glenn said, some of these components have dozens of different things that put them together in the assembly. And so for my thing, what I focused on with a partner, Matthew Rubis, was a redesign of the thumb screw, like Mike was talking about. And so just to give a bit of background on that, what Mike and Glenn came to us with was this thumb screw that had traditionally had a little keyhole at the top of it where the astronauts would use a tool to tighten it down, whether it be on the foot restraint or the monopod for the camera. And so basically now they wanted to be able to tighten it without that tool. I'm not sure if that tool was no longer standard issue carry, but regardless, they wanted to be able to tighten it down sufficiently with just their fingers. And they couldn't do that, especially if they were wearing, thick space gloves on. And so what we had to redesign, Matthew and I, was the top portion of the thumb screw specifically to where they could get that tightness that they wanted to with just their fingers. Yeah.
Okay, so Shane, you were presented just the thumb screw problem.
I think we were presented kind of like a multitude of things, and we just ended up going down that path. We did do some side tangent projects, some smaller scale stuff. But yeah, that was definitely like the main focus of my junior year.
And one of the things that Shane had to do too is with this redesign, he also had to make sure that it fit in the current clamps and the ball clamp assembly itself. So not only did he do that one portion, he had to make sure it interfaced and worked well with everything else.
Right. Well, I know nobody else can see it, but I brought it in because I'm much easier. I'm much better at talking with my hands than just talking out loud. What Shane was handed is imagine a long screw, and then on the top of it, it's got kind of a flower-shaped grip for it. And we thought we had started off. We thought we had done this well because wow, we tested it on lots of stuff, and it seemed to work pretty well. But then after Shane had come back with a much simpler design that was just kind of like a single kind of big tab at the top. I don't know how to describe it any better.
That's correct.
It was so much easier that we could get an extra, almost a full turn out of it because of being able to have a different grip and just a lot easier to kind of grab onto and hold. It made a big difference in this project, but also in future projects. It's funny. Most engineers work on these little tiny things, and when they have to try to talk about what kind of cool things they're working on at home or whatever, people say, "That's all you did?" But it's the most important part because Because when you, if that final connection doesn't work right, then people don't want it.
But and it has that residual effect too, right? You're talking about this tiny little piece on the monopod, but you just said that that design was good enough that now it's being considered for other things because you avoid the need of a secondary tool and you can get extra strength. I don't know. It sounds like it's kind of a flat piece, right?
That's exactly
right. So you can kind of like work your thumb into it.
That's
so,
right.
Yeah, you can apply that to other things.
Yeah. So the iterative process that we end up with, and this happens for all engineering, but it really makes a difference to have these different people coming in, a slightly different perspective, because they think about it a little bit different so that we can all benefit out of it. And we keep trying all of these different iterations to try to make the best one that we can.
So when you present, this is for Mike. When you presented this challenge to Shane, what tools, what resources did you give him and the other students? Like, did you give them mock-ups? Do they have facilities that they can access? CAD software? Like, what tools do they have to actually help out with this?
Well, Shane was in toward the advanced years of the classes that he's in, so he was very proficient at CAD work, and he was using parametric CAD, so he could make the 3D models and he could actually create the files needed to go to the 3D printers that he had. So we came in with a basic package of what we had and then identified where we needed to go with it. So he could see what we had, see the models that we had for the first iterations of it, and then troubleshoot it and problem solve it and come up with one that gave as we said, almost another full turn of torque on that. So, and then he used those skills to do it.
So Shane, how did you approach that? Did you, what was that like when they said, "All right, Shane, take it away, come up with a cool design"? What were some of your first steps to come up with your solution?
Sure. Yeah. So obviously, like Mike just said, we were given the previous iteration and just a general direction as to how we wanted to go from here on out, or where we want to end up at, rather. And so and this is arguably my favorite part, and that's the brainstorming part of it, because you just have so many ideas on where you can take this. And there's a beauty in the creativity that comes with that, but it's also at the same time daunting, because you're like, okay, I have so many cool ideas. Now, which one do I choose? Which one do I invest my time and effort into? And so, yeah, again, like we ended up with the flathead design that gave us a lot more torque. But I remember going through the entire like engineering design process, and I loved every moment of that. Starting with brainstorming and then going through different, like bring it into CAD and iteration by iteration, having like people test it out and see, oh, how does this feel in your thumb? And just tweaking small little things. And like Glenn said earlier, when you come back home and you say, oh, I worked on a thumb screw, people go, really? Like, that's it? But there's so many little things that were so fun about it. Like just changing the different radii of certain edges and the fillets to see which is most comfortable and which you can get like the most surface area of your thumb on it. Different tiny considerations that all add up into a perfected product in the end.
It sounded like because of what you were working on, this thumb screw, right? It sounded like you had kind of an opportunity to. You said you got to play with a lot of different designs, but was it all on the computer, or were you 3D printing some models, testing them out, making some changes, going back into CAD? What was your process?
Absolutely, yeah. It was an iterative process. Okay. So I would create something in CAD. 3D print it, because we were fortunate enough at my high school to have some 3D printers available.
Awesome.
3D print it, and because they're relatively small screws, they don't take long. So after a couple hours, I'll have that batch out, and I'll see how it feels. I'll put it into the foot restraint or the monopod. Make sure that it screws as tightly as it needs to, and then you say like, maybe we can tweak this. And again, I'll present it to Mike or Glenn, and they'll say, yeah, well, we need to tweak this or this or this. And so I'll go back and tweak that, and it's just a recycle of that process over and over and over again until we have a good product.
How many of those do you think you printed out?
Oh, gosh. Probably 3 digits, 3 figures.
Yeah, there were several iterations, because what he had to do, not only was it had to be functional, it had to be comfortable. And you had to look out for, how does this interface? Are we creating stress if we do this design? So we had all that, not only just functionality of it, but is it comfortable to use?
Well, and so I don't know about Mike. I think I probably have 10 or 20 of those still rolling around in my drawer at work.
I'm the exact same way.
Probably have, with that many, probably have multiple thumb
You
screw
betcha.
drills. Yeah, yeah. Shane, you said we when you're doing this. So were you working with a team? Who was your? Did you have did you have folks with you, teachers? Who was helping you out with this?
Yeah, so obviously on the NASA side of things, I had Mike and Glenn, my NASA mentors that I would give my revisions to. But then on my side of things, obviously I had my my CAD teacher, Mr. Gerald Ford, and then I had my partner, Mr. Matthew Rubis, and it was mainly him and I that were working on the iterations and the CAD and 3D printing and so what.
How long did that process take you from the time you started with the initial designs to the print, try again? It sounded like a lengthy process if you're in the 3 digits.
Yeah. So the time from we got presented the project basically at the start of the school year, so August, September, what have you, and then I remember finishing it basically, going through the entire process around the end of that school year. So it would be maybe like May-ish, maybe just before May. So yeah, basically an entire school year was put into this project.
How did you split your time with your other classes?
Are you referring to my other high school classes?
Yeah. Like, was this all this work after school, or did you sign up for some extra periods of 3D printing class to try to get a lot of this done? How was your time spent?
Right. Yeah. So my engineering class, as is, was a block period. It was about 2 hours, as a part of my actual school day, and so of course those 2 hours went into it. And then of course I put time in at home as well, though that's harder to quantify. But yeah, it was mainly done during class time. Now of course I did have other things to do during class as well, but my teacher, Mr. Ford, was accommodable. I'm not sure if that's a word. He was accommodating.
There it is.
There you go.
To let me work on this in class.
Oh, that's fantastic. Yeah, I can relate just a little bit. I was when I was in school, I was really into filmmaking.
Yeah. Yes.
And you find something you're passionate about like this, right? Where you have a couple of hours in school, like you got a period where you can dedicate to, in Shane's case, engineering. In my case, it was film. But I found myself, I signed up for it was my senior year. I signed up for track and field. I never went because I was always in the studio playing with film and getting to, enhancing my skills because I just found a bigger passion with that. Sure. So I think that's when you know that you like something, right? Is if you're doing that. And then you said you put some hours in at home too. I mean, you must have loved this. You must have been like, I got to get this done. This is something that you must have been really passionate about.
Absolutely. Yeah. It was a passion project. It was a project of love. And so, when you're passionate about something, whatever it is, whether it be engineering or film, you find yourself putting more hours into it just because it's fun, right?
Yeah.
And so, yeah, definitely.
Mike, Shane's not the only one doing. This is not a thumbscrew project. This is a whole thing.
Right.
So you are doing this. You must be having this oversight with folks like Shane, right? Who is making redesigns. Go back, try it again, and you have to be doing that with all of the different components of this monopod. Is that right?
Correct.
With all the different students.
Correct. We had students working on the ball clamp. We had students working on the iterations and the hemispheres that go in it to make sure they fit correctly on the handrails. So there were little teams all around in the different school districts around, between, again, from the camera shoe. And once Shane did his incredible work, that was passed off to Mr. Bill Gibson, who's one of our mentors, and he worked with his machinist students, and they manufactured these.
That's right.
So,
yeah, and so, for example, Lorenzo Ferralis is one of our students who was up in Conroe working with Eric Canistorp, and we went back and forth several times. And I've got a whole bunch of those 3D print jobs sitting in my drawer, and we're saying, make it 1 more millimeter here and round off this edge there. But then the machinists also have to be doing some really excellent work. So the students that are going over to do the machining for the camera shoe, the students that are doing the 3D printing for the ball clamp, they all had to be doing some really excellent work for us as well. And they certainly deserve a lot lot of the credit of making this look like a good flight hardware piece.
Where does the integration happen? How do you have all these pieces? It sounds like parts all over the country, really.
Correct.
How do you bring them together into a design and then get it flight ready?
We come up with a finalized design. We have one group of students that, for example, at this school, that came up with what we thought was the best flight drawing, and then we choose the different parts for the schools that show interest in it. For example, our 3D printing school in, I believe, Alabama.
That's right.
Or
Georgia.
Georgia. They are amazing. They produce wonderful parts. They are doing the flight parts, and they take care of that, the documentation and all that. So we know that right now they're the school that we go to for flight. For prototyping, we've got schools also across the country that do fantastic prototyping and get to us for study models, and they can have another pair of eyes on it to see if it works, does it come together, and other suggestions and feedback.
All right.
So it's a huge team effort. It absolutely is a team.
Now, once the parts are machined and we get them all finalized in terms of the surface materials that we want on them and things like that, then they come to one of the schools here by Johnson Space Center, and we have an assembly there. And that's done by Carlos Valencia, and his job, he's a professional assembler. And so he does a lot of assembly work for other NASA hardware, and we use his excellent skills at getting it all put together because there are specific information that we have to put into it. For example, what's the torque value of each of the screws? What kind of epoxy material do we use to hold the threads and things like that? And so, unfortunately, we don't get to have students do a lot of the final assembly work just because there's a lot of detailed work in that assembly process.
That requires a lot of expertise.
And unfortunately, we can't teach it in a year, you know? And so it's something that we've got to have a NASA professional working on.
Okay.
But the students will go through an inspection process. So as they manufacture this, they still go through their inspection process, their documentation, their tracking of materials. So they're still doing that. And then when they send the parts to us, we go through and all that material is there. We may double check the parts, and then they're good to go.
Shane, have you seen the flight ready model? Have you gotten a chance to take a look at it?
I have seen pictures. I have not seen it in person. Granted, I've been in Austin, away from the Houston area for the past couple months. But yeah, I've seen pictures.
That's awesome. So I guess what comes after that? Now you have someone who has the expertise of getting it basically ready for flight.
That's
and
right,
then
correct.
comes the job of manifesting. So do you just have one monopod that's going up? You got a fleet of them? What's going up?
Right now, we're sending up one.
Okay.
The crew are going to evaluate it, tell us what they think. We have hopes that they might want another one, or that it might fly on some of the later vehicles. So, for example, the Gateway might want one for similar kind of reasons. And so we're just hoping to be able to, I think what we're going to do is probably build like 6 of them total, because we also have to have some on the ground for training and other testing for different procedures and things like that. And so we'll probably we're going to have several to be able to hand around to different places.
Right. This is going to be launching soon, right? This is
SpaceX 27 is what it's slated for.
That is coming
That's
up.
exciting.
It's very soon, so I think we're talking March 12th is the last I heard. So.
Yeah, I think by the time this comes out, SpaceX 27 will have already launched. So it should be, I mean, I don't know where we'll be at. Maybe they'll have tested it or what, but we'll at least have a nice preview. You guys, this has got to be a pretty exciting time when it gets manifested. What are generally the students' reactions?
We try to contact everybody that's worked on it and let them know, and they're just so excited that what they worked on, because it's a multi-year process.
Yeah.
It is a multi-year process. And so we always try to communicate back to them and their teachers that all that work and all those iterations that Shane went through and everybody else went through, that here it is, it's paid off, and now it's actually going to fly.
Shane, how do you feel? You're one of those people. You actually contributed something that's going to be going to space.
Yeah. It really is a dream come true. Like I said in the beginning, it was a goal since the first day of my freshman year. And I remember when I got the call from Mike saying that it was going to be on the flight out, that like when I went home, it was towards the end of the day. And when I got back to my car, I just sat there in the parking lot and screamed for a couple minutes. I remember calling my girlfriend and my mom and my dad and my best friend, and just saying like, it's finally happening. It's finally happening. And yeah, it just, even now, like it makes me so giddy. I have such a huge grin on my face right now. It's so awesome.
Wow, that is unbelievable. This, Mike, this has got to be probably one of the best things about this program is,
Absolutely.
you said it's a multi-year process, right? And I don't expect it to be easy. With that amount of coordination that's happening, with all the process, it's very lengthy. Yes. But the reward is this. The reward is a student kind of jumping for joy in the parking lot. That's
absolutely.
I mean, that's worth it.
Absolutely. It is about the students. Absolutely.
Yeah. That opportunity is absolutely amazing. So yeah, it sounds like this is something that you already have deeper visions for as well, right? So this is what we're doing is sort of a test. You're going to get feedback from the astronauts. Oh, it's a little too loose up here, or hey, I would appreciate a couple more inches here. I'm guessing that is a whole process of feedback that's going to be happening.
That is exactly right. So, and we've had other things where they fly up and the crew says, this is really good, but we'd like this changed. And so we have projects that keep coming back to us. But the other thing that we get back is that the crew call down and they say, these hunch projects are really working out well for us. And if you go online with us, sometimes you'll see that there's crew talking about, hey, this is something that the students of this school sent up to us, and we're really liking how this works. It's terrific for the crew because they feel like they're reaching right back down to earth and talking to the students directly about what they really like about the space station.
This is something that's, I think, more visual in terms of hunch projects as well. I mean, this camera mount, Glenn, you were sort of laying out sort of what the vision is for how it's going to be used. We're going to see a lot of pictures, video. You talked about, I don't know if this thing can hold teleprompters or what, but there's a chance that if the astronauts really like this and you start sending more up, they could be using these all the time.
That's exactly right. Right now, they're using what we call a multi-use bracket, which is it's a great tool, and you see them all over the space station. Mm-hmm. But as great of a tool as they are, they don't fit every function. And the same thing goes for this, right? It's a great tool. How many different functions is it going to fit? We really don't know yet. I mentioned being able to get right into the middle of the module because it's long enough to be able to do that. But the other thing that one of the astronauts had mentioned to me was how when you're in the cupola looking down and trying to follow a particular object on the ground, let's say it's a volcano is going off, keeping yourself steady and being able to follow it as the space station flies over, it's really helpful to have something to be able to kind of slowly pan with. And we hope that this is going to be helpful for them to be able to follow objects on the ground, as well as being able to keep it steady when they want it steady. So we'll see how this works out. Another place was when they're using the glove box, the microscience glove box.
Oh, yeah.
Being able to get into the right window and position so that they can see what kind of experiment they're working on is also really helpful. And so we'll see how it works out, but we've got a lot of places that crew think that it might get used.
That is very ambitious. This is a really interesting project. Mike, when you talk about the Hunch project and you talk about the benefits of it, what are some of the key things that you try to communicate to students, to, the space station program, to others that want to get involved in Hunch and do stuff like this, stuff where you can be working on, it could be simple as like a thumb screw, but it could be on something that is used all the time on space station. It can be something that's almost, you could even call it critical, and a step forward for space exploration. How do you pitch it?
Well, the first thing we try to tell them is they are part of our team. Just because they're working on maybe something small, or just because they may be a sophomore in high school or a junior in high school or even earlier in high school or other grades, they are part of our Hunch team. and their contributions are invaluable, and they're working toward a real solution. It's not just a hypothetical. They're working in the real industry right now. And we want them to gain as much benefits out of it themselves, too, through exposure to subject matter experts that work with, and just gain some interest in it and see which direction it may carry them.
Are you or any of the students planning?
Sex vehicles land, and so that'd be really exciting.
Oh, yeah.
And I think it'd be terrific if it's launching when it says. I might have some time at that moment, so I'm going to give it a shot.
That would be great. Usually I'm stuck here to work missions from Houston, and I say stuck, it's awesome in its own right, but I don't get to see the smoke and fire out it. And I did get to see it one time, and it is truly spectacular.
Yeah.
I would highly, highly recommend it.
Shane, are you interested?
Absolutely, yeah. It's actually the very beginning of my spring break, so I should also be.
Okay.
Should be good to go.
Okay.
Road trip. Road trip. All the way down I-10. Yeah.
There you go.
All right. Shane, what's your ambitions? You're going for mechanical engineering. It sounded like you were into cars and automotive industry, but how you gonna take what you learned from Hunch, apply it, and what's the next dream for you?
Absolutely, yeah. So Hunch has given me invaluable experience, real industry-grade experience, and I'm applying that each and every day to this day in an organization I've joined called Longhorn Racing, which is basically a organization where students make an FSE car. FSE, I believe, stands for Formula Society of Automotive Engineers. It's like an F1 style race car, and this goes on all across the world, even in Europe and Asia. And we all compete in the summer in, I believe, Michigan, and have different dynamic events and basically put our cars to the test. And we're scored and judged and so on and so forth. But yeah, I'm applying that knowledge, applying the skills that I learned in Hunch in my future endeavors in LHR, and I have no intention of slowing down.
That is
great.
awesome.
That's great.
That is
what
awesome.
a cool project to be a part of. Oh, that's great.
Hey, Shane, have you seen any other Hunch students when you're in college now?
Not to my knowledge, but then again, I don't really go around asking, right?
You're not wearing your
But,
Hunch
yeah.
patch? Come on.
Oh, you're so right.
I
You're
think
so
the
right.
expectation, Shane, is you got to be wearing that at all times.
That's right.
Yeah.
That's right.
True. Very true.
Awesome. Well, hey, this was so fun to be talking to you guys today. This is very exciting. It's going to be launching very soon, and you guys are going to be getting feedback on this monopod
correct.
from astronauts from space, something that could be used all the time. Kind of wanted to go around with just some closing thoughts, closing words. Mike, we'll start with you. Just on, I like to end this way sometimes, which is just the idea of exploration and space and all of that. You know, like for example, Shane going for, you know, having a interest in cars, but being subtly influenced by space. It's something that to me is it is very transferable in that space exploration is a little bit about, you know, exploring and doing new things, but it could be these pathways to very interesting places. Not everybody has to go to space. Not everybody has to go out into the cosmos to explore their passions, but it has this interesting path to get people there. This is just sort of my rambling, but I wonder if you have more thoughtful words than me.
Well, and again, I've just seen what this program and what these type of activities do for our students.
Yeah.
The confidence it gives them, the direction it gives them sometimes, and sometimes they may not go into the direction we think, but those skills they carry with them always. And I think it just improves everything. It gives them a confidence, like I've said, that they may not have had when they came into the program. It gives them a passion, as you can hear in Shane's voice.
Yeah.
And it's just a win for the students, I think, and for us too.
Glenn, what's next for you? I'm sure you're talking with the astronauts, thinking about they're giving you some feedback. The engineers are wanting some projects. What are your?
Well, you know, so we are working on. I've got 3 projects on my desk right now. All of which are, you know, first we start off with what do the engineers need, and then we start handing it out to students to help us out with. So, I mean, we have a project potentially for the Orion vehicle going around the moon, which is exciting. We have things to help out on the space station, and all of these things are little things, right? And the value of that is that engineers all understand at some point that the space station, the space vehicle, whatever it is that you're building, it all starts off as one bolt, one rivet, one panel at a time. And every one of those is contributing to what that final vehicle is going to be like. And so we hope that our students get that same kind of feel, that they are making a difference in what that space program is going to be like in the future.
That's wonderful. Wonderful words. Shane, I'll end with you. And, I'm thinking about, you seem to have an immediate passion for this early in high school, and you pursued it, and it kind of influenced to where you are today. But I wonder if you have some words of advice to, students that are in their first year of high school and maybe not sure of where they want to go, maybe scared of trying something new. And I wonder what piece of advice you have for them.
Absolutely, yeah. So the two things that come to mind, one is get involved. Regardless of what programs your high school has or doesn't have, find something. If there isn't anything, make something yourself. And find something that you're truly passionate about it, and be great at it. Excel at it, and it'll come naturally to you, because you'll want to put the extra time in. You'll want to go the extra degree. So first thing, get involved. Second, you mentioned if you're scared or something like that, find a mentor. For me, it was Mike and Glenn, and I'll forever be grateful to them. Just find a mentor, find someone that knows something that you don't, knows or has done something that you want to do, or something along those lines, and connect with them, build a relationship with them. And if you can align your interests with the interests of others, things are going to work out for you.
Wonderful. Oh, this was such powerful ending words from all of you. You guys are so awesome. This was so fun to be talking to all of you today. Very exciting. I'm happy for you guys to all that work, and now you have the monopod going up to the space station. It's going to be tested out. Very, very exciting, and I'm glad to have all three of you on today. So I appreciate your time.
Thank you for the opportunity.
Thank you so much. Yeah.
Thanks a lot.
Houston, go ahead.
Stop of the space shuttle.
Roger, 0G, and I feel fine.
Shuttle has cleared the
Became
tower.
a peace for all mankind.
It's actually a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Never Houston. Welcome to space.
Hey, thanks for sticking around. I had fun talking with Mike, Glenn, and Shane today, learning all about the camera mount. Very cool stuff to be hearing from the team, and how long it took, and the passion that they have for creating something and contributing to human spaceflight. I really hope you enjoyed. You can check out Hunch at www.nasahunch.com. And then you can also go to nasa.gov to find Hunch and some of the other resources and opportunities we have with students, and then, of course, a lot of the things happening aboard the International Space Station. If you're into podcasts, though, don't worry. We have a lot of them at NASA. You can just go to nasa.gov/podcast. That's where you can find us. Houston, we have a podcast, and our full collection, as well as other shows we have across the agency. If you want to talk to us on social media, we're on the NASA Johnson Space Center pages of Facebook, Twitter, and Instagram. And on any one of those platforms, you can use the hashtag AskNASA to ask a question. And if you want to reach out to us specifically, just make sure that in your question you mention us. Houston, we have a podcast. This episode was recorded on February 17th, 2023. Thanks to Will Flato, Pat Ryan, Heidi Lavelle, Belinda Polito, Jaden Jennings, Aaron Anthony, and Rachel Berry. And of course, thanks again to Mike, Glenn, and Shane for taking the time to come on the show. Give us a rating and feedback on whatever platform you're listening to us on, and tell us what you think of our podcast. We'll be back next week.
Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 263, A Delicate Balance. I'm Pat Ryan. On this podcast, we talk with scientists, engineers, astronauts, and other folks about their part in America's space exploration program. And today it's scientists as we get into the details of what being in space does to your puny human body. The most obvious consequence of your being off of the Earth and in the reduced gravity environment of space is as plain as can be. You float. Now, speaking for myself, and I think most of the rest of us, that would be outstanding. But beyond the gee-whizness of you floating, and also past the concerns surrounding, well, how do I work when everything else is floating too, there is another concern that is both immediate and long-term, and that is, what effects does reduced gravity have on your body, on your health, right now and potentially down the road? Since even before the first American flew in space more than 60 years ago, scientists have been working to answer those questions and to develop countermeasures to those deleterious effects so men and women in space will be able to do work. Today, we're going to talk about that with two NASA scientists at the forefront of the research into the effort to make space safer for the humans who go there. Dr. Scott Wood is the Neuroscience Laboratory Manager at the Johnson Space Center and the lead scientist in the sensory motor science discipline. He earned his doctorate in the Department of Otolaryngology at the Baylor College of Medicine in Houston and has participated in flight investigations since joining the Neuroscience Laboratory in the 1980s. He now serves as a subject matter expert for NASA's Human Research Program and the Crew Health Countermeasures team. Also with us today is Dr. Mil Reschke, recently retired from the Neuroscience Laboratories at JSC after a NASA career that began in 1972. Think Apollo astronauts. He earned his doctorate in sensory physiology, psychophysics, and vestibular and audio function. And his NASA work has centered on, well, actually it continues to focus on, because he's still working, even though he retired. He's focused on changes to the human sensory motor system during and after exposure to long-duration spaceflight, as well as the development of countermeasures to be used on future such missions, including the ones to Mars. The Sensory Motor Guidelines for Future Exploration. Here we go.
T-minus 5 seconds and counting. Mark. Mission start. T0. Launch commit light circle correct. There she goes.
Houston, we have a podcast.
I'm not sure who was the first person to recognize that there was no gravity in space and that the conditions there weren't necessarily ideal for human beings whose bodies evolved to live in this perfect pull of gravity that we've all known all of our lives. But while the United States and the Soviet Union and Russia and other nations of the world have been putting people on rockets and sending them out to space, they've also been working to understand how the conditions in space affect people and what we can do about that. So I'd like to start by getting into some of the details of those effects. Scott, what effect does the lack of, for lack of a better term, normal gravity, our normal gravity, what is the lack of it? What is the effect that it has on human beings in space?
So that's a great question. It really affects a lot of different systems. There is some deconditioning that occurs in the musculoskeletal areas. The cardiovascular system deals with the shifting of fluids that goes headward. Our interest in the neuroscience lab has been really focused on what this means in terms of your body's ability to orientate yourself, sense motion, and control motion. So we have some specialized gravity receptors in our inner ear that normally detect your orientation relative to gravity. And so when you're in weightlessness, they're providing a different signal, so the brain has to recalibrate what information it's getting from those sensors.
Is it a different signal or the lack of a signal?
It can be a different signal.
Okay.
You could think of it that way because you're still moving about, you're still accelerating. It's just the cues that you're getting are different, and especially the way you combine cues from the different sensory systems like vision and your ability to interact with your support surfaces is completely different. You're not having to offset the weight of your limbs as you reach for things and as you move your legs. So just the way you interact with your environment is completely changed.
That would have a tremendous impact on doing any kind of task, wouldn't it, Mil?
Oh yeah, yeah. The issue that we struggle with in trying to do this kind of research is removing gravity before they ever fly into space. And one of the tools that we have and that we brought back to NASA early was parabolic flight.
Right.
And that's the first experience that most people have with removing gravity and having to interact with the situation that you are going to occur in space flight itself.
Well, we talk in training astronauts, we try to create the conditions that they will encounter. But what you're saying is that gravity is such a condition that it's damn near impossible for us to remove it, to let people see what that's like, right? Explain how the parabolic flights mimic that condition.
Well, most people think that the airplane just dives. It doesn't. It does, in fact, dive rather dramatically and then pulls up. And it's the pull-up when you reach a gravitational state of zero for a period. Depending on the velocity of the airplane, it can last anywhere from 20 to 30 seconds. Do that over and over again for as many as 60 parabolas. And it's very interesting to watch people that are experiencing it for the first time.
Now that's 20 or 30 seconds at a time, but when you do it 60 times, that's not all consecutive, right? You feel gravity again in between them.
Yeah. Generally, depending on the amount of time that you spend in a weightless state on a parabolic flight, is related to the amount of gravity that you have to pull. So the higher the gravity during the initial pull-up is going to range anywhere from 2.5 to 3G.
Let me back us up a bit here. When did NASA start investigating how weightlessness impacted the sensory motor functions?
I don't think when NASA began to first consider putting people into space that weightlessness was really a big consideration.
Mm-hmm.
And it only became more of an issue throughout the later Apollo flights, and certainly the Skylab missions, the shuttle flights. And then as duration increased in terms of how long they were going to remain in a weightless environment, NASA did realize that we had a problem. Mm-hmm. And the problem was, how do we essentially condition people to fly in a weightless environment for a long period of time? The answer to that is we really don't.
Yeah.
It's
because we can't mimic the condition for them long enough?
Yeah, you're basically the only kind of tool that you have that allows you to do that is parabolic flight. And NASA canceled its parabolic flight program several years ago.
Right. Let's stay back in the past first. Mill, tell me how you got interested in and involved in this research in the first place.
Well, it all started in graduate school.
Yeah.
I had a very good professor who had, in fact, done a considerable amount of work at Wright-Patterson Air Force Base. And I became his student and did work at Wright-Patterson with him. That's the first time I met an astronaut was at Wright-Patterson. Story
When was
Musgrave.
that?
Yeah.
When was that?
Oh, gosh. I've been at NASA for 50 years.
Right.
That was way before that.
Mm-hmm.
The late 1960s.
1960s.
Yeah.
And how did you get from that situation to coming to work at NASA?
It was an accident. I had graduated from Miami University in Oxford, Ohio, and was just looking for a job. I got a teaching position at Franklin Pierce University in New Hampshire. I was never a teacher, and fortunately, after about a year, or less than a year, actually it was one semester at Franklin Pierce, I got a call from NASA saying, send us a resume. We'd like to maybe give you a job.
Mm-hmm.
And that was in 1972.
What was that first job?
First job was really just following people around and looking. We actually those were the Apollo flights, and we were beginning to test people, their balance before flight and after flight, as well as looking at vestibular function in more generalized clinical ways. And basically, that was how I started. The laboratory here that I had when I first began to work was dedicated more to sleep and some other brain functions. The primary equipment that was available at that time was a bed. And
high tech.
Yeah, and a soundproof room.
Outstanding. Scott, while we're on the subject, tell me about your educational background and how you ended up here in labs that had more than just beds.
That's right. I came at the beginning of the shuttle program, or early in the shuttle program, when motion sickness was starting to become more of a concern with these shorter flights. And so I joined Mill. I worked for Mill, and he mentored me in my early career between undergraduate and graduate school. So I just really fell in love with the subject matter and wanted to do more. And so I pursued my doctorate degree at Baylor College of Medicine so I could remain affiliated with the lab. I've departed on occasion. I went and worked for a little bit at a nonprofit hospital in Portland, Oregon, and in the same field, and looking at vestibular disorders. I worked with the Navy in Pensacola, Florida, where some of this early space research was done. So I got to be part of some of the work they were doing in military aviation world. Did a stint in academia, but I keep coming back to the lab here.
There's an attraction.
There is an attraction, and it's just a very fascinating area.
We were starting to touch on the beginnings of this research. Take us back to that point. Tell me, how were some of the first ways in which NASA began to study how astronauts were affected by the lack of gravity?
Well, that's a hard question. I think that what was observed was that as the flights became longer and longer, it was apparent that returning back to Earth was not simply a process of walking out of the spacecraft and continuing to go about your daily business. We were seeing difficulty in walking, difficulty in situations where vision wasn't available to the returning astronauts.
Where vision wasn't available?
Yeah, well, when you get into a darkness or a situation like that, you rely in those kinds of conditions on your vestibular system in many cases.
To understand which way's up.
Yeah.
Among other
Which way is up? Which way am I turning? You know, Why do I feel dizzy when I turn my head to the right or left or look up or look down? I'm losing my balance. What do I do?
And at that time, we're starting to see more astronauts who are experiencing more difficulty than prior astronauts had.
Yeah, it's a matter of how long you spend in a weightless state in terms of the duration that you're going to see in terms of vestibular function returning to a normal Earth environment.
What's the thought about why that is? I not having done any of this research, of course, myself, I can see how not having the cues of gravity would impact you, but apparently it continues the longer you don't have that effect, that impact. Do we know why that is? Does your body forget, or what is it?
I don't know if the body forgets it, but the body has to reacclimate to the environment where it's a normal gravity.
Mm-hmm. I've heard astronauts who've been in space say that once they get there and they become acclimated to the lack of gravity, that they function perfectly fine. But when they return to Earth, their body then encounters it again. Both of those things sound to me like the body's doing a terrific job of adapting to the circumstance it finds itself in.
And that's the point, that the most profound effects from some of this adaptation occurs very early. That's when people experience motion sickness. But as you point out, after a few days to weeks, that effect is lessened and people adapt to that new environment. There is some period of time that there's a slower adjustment just to being able to be more proficient with the way you move and things like that. You can tell a difference between crew members that have been in space for a few months, for example, versus a rookie crew member that just arrived, and they can tell a difference. That they'll describe that sensation that they're realizing that they're able to move more efficiently. But I think that you're right. The body's doing a wonderful job adapting, but all that adaptation for moving efficiently in microgravity is not necessarily helping you when you have to when you re-enter a partial or a full gravity, Earth's gravity.
Or because a different gravity environment.
The brain, that's correct. The brain has to, again, reset, recalibrate what information it's getting from those sensory systems. And it's an integration of all the different sensory information that you have. And
you both have touched on this. The point is that the brain is using it's what it understands about the environment that you're in to allow you to function, and it is smart enough to be able to know things are different, so I have to act differently. Is that an awful way to explain it?
No, I think that's a really good way. So actually, part of what we also observe is that process of adaptation is dependent on how you move when you get into that environment. So there are certain things when you're reintroduced to Earth's gravity that you probably want to avoid doing, like making large head movements relative to gravity. That can be pretty provocative, and you discover that pretty quickly. And so there's some
provocative meaning
evoking motion sickness, leading to vomiting. Yes. So there are certain movements that people will try to avoid when they're going through that early parts of the adaptation. And so part of what we're researching is really looking at how we can help crew members go through this period, be more efficient in terms of incrementally exposing themselves and adapting to that new environment. Because there are smart and not so smart ways to reintroduce yourself to this gravity environment and hasten that adaptation.
Well, let's expound on that for a minute. What ways did we years ago tried to allow people to readapt that we found that worked and that didn't work?
Well, I think in terms of the readaptation, exercise programs have always been one of the primary tools. That's not necessarily in our field, but it does force people to move. And the more you move, the quicker you're going to be adapted to that environment.
Are you thinking about exercise while still in space or after you've returned?
Primarily after you return.
Okay.
Exercise in space can actually be detrimental to the vestibular system that you're going to experience the movement. It's beneficial in helping you to adapt to that environment, just like it is when you return to Earth.
And I guess the exercise is good in allowing your muscles to keep working in that environment, but you're saying it's not helping your sensory motor system.
No. As a matter of fact, the vestibular system has a profound effect on the sensory or the postural muscles, the muscles, particularly in the lower part of your leg.
Yeah. Tell me, how so?
Well, it's a direct connection from the vestibular down to those muscles through the brainstem. And if the vestibular system is not functioning the way you would like for it to function in a particular environment, it will definitely have an impact on the way those muscles respond when you try to move. Most people don't. It's very difficult to explain to people what the vestibular system does. But
give it a shot,
because there's very few examples for sitting here around a table or moving anywhere. You don't know about the vestibular system. It's very silent. It works very, very silently. Only when something goes wrong with it are you aware that there's something that is happening that is not beneficial for me.
When you become ill in some way.
Yeah, when there's some...
And you lose your balance.
Trauma or disease that affects the vestibular system. Most people don't even realize that they have this system. It works very well. I usually use an example of people seeing the vestibular system in action is I have them hold their hand out in front of their face by about a foot or so, and to shake their head back and forth at about one cycle per second, and look at the lines in the palm of your hand. Now that activates the semicircular canals, the part of the vestibular system that essentially responds to angular acceleration.
Okay.
But after you've done that, then shake your hand back and forth, and the palm of your hand is blurry. And that's because the vestibular system is making the eyes move and remain stabilized in space.
Okay.
So that's a way to learn something about the vestibular system, because it's very quiet, and like I say, you don't know that anything you have a vestibular system for most people until there's a disease process or some other thing has caused the vestibular system to not function properly.
Can you describe where in us the organs of the vestibular system are, and which I think will give me a sense of how they would be impacted by the lack of gravity? We've started in the ear, right?
That's the ear has three major organs: the auditory function and the vestibular, and the vestibular system is comprised of it. For simplicity's sake,
please,
a system that responds to angular acceleration and a system that responds to linear.
And forward or side to side.
Right.
Okay.
Or up and down.
All right.
Yeah. Mm-hmm.
So knowing, I'm trying to think of an example. Anybody who's ridden a roller coaster, I'm thinking, probably has some experience of how their relationship to their environment changes based on the fact that their body is in a different situation. Is that a good start, Scott?
Yeah, and our inner ear function, our vestibular function, is adapted to kind of normal movements. So as you point out, when you get in something maybe a little different than you're normally used to experiencing, like a roller coaster, or some of us have played this game where you spin around in circles with your head on a baseball bat, and then you try to run a straight line or something like that. That's not the way we normally move. So, and the vestibular system provides some signals that make that challenging, that test challenging. I want to get back to something that Mill did say, though, about exercise, because we have seen that some of the advanced exercise programs that we have on ISS do help you in the process of recovering, so that maintaining that muscle conditioning, and there's some conditioning in terms of the sense of joint position and things like that can be helped by that in-flight exercise. Our challenge now as we move to exploration, we won't have the space that we have on ISS for this wonderful gym with advanced aerobic and resistive exercises. We need to be able to downsize that, and that's I think going to be a very big challenge for us. How can we maintain that conditioning on these long duration space flights?
Right. The International Space Station has a whole module that is filled with some pretty remarkable exercise equipment that you don't have room for inside an Orion capsule.
That is correct.
But I guess we could plan to build it on lunar outposts. That we would have more stuff that we could put into bigger rooms.
Yeah, this is a challenge for us. How much do we really need? What are the critical components? How can we make it more efficient? And for us also, then once you arrive, what can you do to assess the individual in terms of helping make sure that they are in a good condition to go do the tasks that we have them to do? One of the things that we haven't touched on is that there's a wide variability in responses among crew members, just like there are in those of us that ride those roller coasters. Some of us enjoy them and some of us not so much. So we have folks that are more impacted than others in terms of what motion sickness symptoms they experience or how long it takes them to recover. And so that's part of our challenge too, is how can we provide the tools just to be smart about making decisions about when people are ready to perform different tasks. How can we structure tasks so that people are set up for success? What aids can we provide that enable that successful performance?
And you're talking about performing those tasks while still in the space environment.
Or in a partial G environment, for example, landing the vehicle or getting out of the vehicle or doing some of the early EVA tests.
And your point a moment ago is really that not all astronauts are created equal. Given the same set of circumstances, one astronaut may respond to one degree, and another astronaut in the same circumstances would respond differently, better or worse, but it's variable. It's not all the same for everybody if you've been gone for 5 days or 5 months. Is that right?
That is correct.
Yep.
You were about to say something, weren't you?
No. No, Scott covered that really well.
Do you find that there's a a relationship between how long an astronaut is in this environment and how much of an effect it has? Or, to use your example of all astronauts not being created equal, that it's a function of the individual rather than the amount of time?
There's definitely effective duration, as Mel was pointing out. We know, if you think about the Apollo mission, for example, that we had 4.5-day transit to that lunar surface. So that wasn't a very long time in which they adapted to that microgravity environment. So that was analogous to some of our early shuttle flights.
Mm-hmm.
But the shuttle flights went up to 18 days in duration. And as those shuttle flights became longer, and as we had other long duration experience with Skylab and, of course, now on ISS, we have definitely seen a difference. We have some plans within the human research program to actually look at these responses over longer periods of time, like with 1-year missions.
Right.
So this is really critical for us to understand that effect of duration, because it's going to be a longer transit to get to a Mars surface. And so one of the design reference missions we're looking at for Artemis is keeping people on the gateway for a period of time so that we can mimic some of those longer transit times before they come to the lunar surface, and we could evaluate what we need to do to protect crew health during those longer transits. So that's a really important part of the program, looking towards Mars and preparing that Mars architecture for success.
And I'm you correct me if I'm wrong, but this touches on the research in a white paper that you guys shared with us about the studies that you're doing, not only of how astronauts are affected in the space environment, but how they're affected in a partial gravity and then a full gravity environment again, because we are sending them on a mission where they may encounter all of those different variables, but we still want them to do work at all the different stages. And we need to be able to know how to help them still be in a condition to do that work. Is that a summary of it?
Yeah, there are, knowing what challenges crew members are going to have, and we've been studying that and we continue to study that. There are a number of things that we can do to help them in that state. We can be smart about how we're planning these EVAs, so we can put things that are maybe more challenging a little bit later and try some of the more simple EVAs up front. We can give them tools that help assess their ability to do the task, give them tools that help them be able to enhance their recovery. And of course, as we look towards exploration, we have a lot of people helping returning crews right now when they come back from ISS. There's a lot of resources that we can bring to bear to even help them in the recovery process, coming out of the capsule and so forth.
Right,
but we need to think more autonomously as we think about going back to the moon and onto Mars. We have to come up with self-administered tools that they can do and help enhance that recovery.
The ways they can take care of themselves and each other.
That's correct.
Because they're going places where there aren't recovery crews to help them.
That's right.
Give me a summary of how your research is pointing. What are you finding about how people are impacted and how I guess I don't know the right way to ask this question, of what we can do to help make sure that they are in a condition to take care of themselves and to do their work at those various stages of a mission.
I would like to say, just to
Sorry,
introduce
I didn't mean to look at that. Go ahead.
Well, to introduce to address that question, I think Dr. Eschke has actually led one of the real pivotal science experiments that addresses this, the decrements that people have in that recovery process. So he pioneered a study that was a collaboration with our colleagues from Russia, and we were going out to the landing places in Kazakhstan and partnering with our medical professionals. They were a great asset, and of course the crew, to support these experiments and participate in them. So while they're just moments after being extracted from the capsule and carried to the tent, Dr. Reschke was
in the tent,
not in the tent himself, but he was behind the studies that we were doing early post mission. So this was really critical for us to get a good characterization of what those decrements were, and what we needed to be mindful of as we kind of go forward for exploration. So having said that, I'll turn it over to Dr. Reschke.
Yeah. Well, I'm not sure where to go from that, but what we were doing in terms of testing crew members returning, as soon as they could be taken from the space capsule, was to make the testing that we were going to do essentially unavailable to anyone to watch. So the Russians were very helpful in that, providing
the tent.
The tent. Mm-hmm. We owned the tent, mm-hmm. and that meant that even the Russian generals weren't going to come in there and watch. And we did very simple testing. Can you stand up from a seated position? And what happens when you do that? Can you walk heel to toe, for example? Can you get up from the ground after you've lain in that position for several minutes? And what does it take to stand up? Very simple things like that. Turning a corner, walk and turn a corner.
They do sound very simple.
They are very, very simple and very, very challenging.
They are.
Yep. Very challenging. It's interesting to watch the progression of the recovery, which we were able to do, particularly since we began testing in the field immediately after landing, and then on the U.S. side, testing again during the period of time when the plane was returning and being refueled in Europe.
Bringing astronauts from Kazakhstan all the way back to Houston.
Right.
During that period.
So we tested again a few hours later in Europe, and then we tested again when they returned to the U.S. And that was generally just a little under 24 hours.
Right.
That the last test was done. And then we tested every day as much as we could over a period of time until recovery looked like it was fairly complete.
Is it a kind of a template of how people recover in that way, or is it, again, your mileage may vary depending on your astronaut?
Well, it depended on the specific crew member in terms of how fast they could recover. I think that what we've seen over the years is that the longer you're in space, the longer the recovery time is going to be.
Okay.
Apollo astronauts recovered very quickly, typically. And the shuttle astronauts recovered almost like the Apollo astronauts. Within a day or two, most of them were functional. But then when we transitioned into the space station and longer durations, what you see typically is a period of time of 6 months is a break point.
Meaning
that
6 months until they're functioning normally?
No, meaning that if you've been in space for 6 months, you're probably going to become having more difficulty from a vestibular sensory motor point of view. and those periods lasting a year take the longest time to recover.
Almost a direct relationship.
But the recovery depends on what you're asking them to do. So if it's the simple tests like standing up, that is a fairly quick recovery. If you have a more involved task that involves some going around obstacles and turning corners, we like to do the tandem walk. You could think of the by the roadside drunk test.
Oh, okay.
Hopefully you've never experienced this.
I've seen it on television.
Yes, of course. But, something challenging like that, and especially if we have them close their eyes, as Mel was mentioning earlier, with your eyes closed, you have more reliance on the inner ear to help you with your orientation. So if we put people in those conditions, the performance takes a little longer to recover on those tasks. So, and that informs us in terms of when we think about tasks that we're going to ask crew members to do during early EVAs. We need to be strategic about what aids we give them to help them do their task as we watch and observe their recovery and to the new environment.
Yeah, the EVAs, that's an interesting point. EVAs are typically not permitted until 3 days in a weightless environment, primarily because of the potential of vomiting.
Right.
And if you're in a spacesuit and vomit, there is a fairly large chance that you're going to aspirate some of that vomitus and die.
Yeah. Clearly not a condition that you want to do everything to prevent.
Yeah, that's probably more than I should have said, but it's
let me ask
there
this.
are limitations. Yeah.
As you were describing it, and it seemed like a direct relationship between the longer you had been in space, the longer it took for you to recover. It occurred to me to ask if you're going from a microgravity environment, say in transit to Mars, and then you're in a partial gravity environment on Mars, do you recover enough to work in that environment as opposed to needing to recover to work in a one gravity environment of Earth? Does that direct relationship between the level of gravity also translate into the time it takes to recover your ability to do what you want to do?
We don't know. The only model we have is, the time spent on the lunar surface.
Right.
And those were very brief stints. We've never had the chance to look at anybody returning after they've spent a great deal of time in a partial gravity.
Yeah, never more than a couple of weeks, less than that.
Potentially, the effect will be less dramatic in terms of return after you've spent a lot of time on, like Mars, surface of Mars, or even the moon. But we don't know what it would look like in terms of the recovery curves.
What have we learned to do to help astronauts counteract the effects of reduced gravity so far?
So I think there are a number of things that we look at doing in terms of, we alluded to this earlier, just procedures. We know that we can address what is asked of crew during these critical times of early adaptation, reduce some of the activities, simplify some of what crews are being asked to do. There are a number of engineering type solutions in terms of handholds, mobility aids, and things like that we can look at doing to make the risk of impairment less, to help them be able to do their tasks. Certainly, we're doing some work with the ability of crews to take over an automated landing, for example, and do that successfully in terms of providing the right training, the right displays, all of those things. Certainly there's different procedural things, we can do in terms of having the task workload among crew members and being able to help each other and manage some of that.
That was, I think, a real good example, too. You're talking about astronauts piloting a spacecraft to land on the moon or wherever. This could be a task that befalls to somebody who's been impacted by being in a microgravity environment for months. And we know from the research that we've talked about here that their abilities to function may be reduced to some level from what they were before they started. And now they're asked to do a really difficult and delicate task. And we have to find some way to make sure that they're capable.
Well, throughout the course of NASA putting people into space and landing, we've typically always had the capability of an automated landing. It's been rarely ever used.
Mm-hmm.
An astronaut's an astronaut. They're going to want to fly the vehicle.
They have no problem with grabbing the stick.
Right. And so it's I suspect that in the future, nothing is going to change that.
But these landings were successful largely because of how we trained the crews, and we trained them very well. We trained them with a variety of different platforms. They had fixed space simulators. They had in-flight trainers. We had that for both Apollo and for shuttle. As the duration started becoming longer for shuttle, the crews were also using some onboard trainers to kind of maintain proficiency. So the key is to have that training level up so that if you do have that disruption, you're more prone to, for example, having disorientation or just some challenges with that cognitive workload. As you're going through that adaptation, you'll be able to handle that task.
The fact is we're aware of what the human astronauts' conditions might be, and so we've built the mission to be able to help them.
That's right. Just simple things like making sure the displays are situated so they don't have to move their head a lot. Having a handhold right below a display that they have to interact with, so they're not having to reach out and touch without. They have a way to stabilize their hands. So what we know from the deconditioning, we can begin to start talking to our providers.
Back into the design of
exactly, and how can we design things to maximize success? What skill sets do we need to train crews to? What resources do we need to be able to stand up so that folks are adequately trained and confident in what they're doing?
Are those kind of things happening in designing Artemis missions now?
They are. We are actually working with our flight operations team and within the research team to try to be very synergistic in terms of raising up some motion simulator platforms that we could look at some of these countermeasures, like training countermeasures and things like that. So there's a lot of exciting work to be done as we approach these missions, especially as we think about these missions with the longer transits before they do land on the moon.
So are there features being worked for these future spaceships that are going to go to Mars, or the habitats or the space suits that the astronauts would wear that would help them in these different environments on the moon and on Mars?
Yes to all of the above.
Okay.
Yes, we have quite a bit of work in a variety of different platforms. We have people researching and looking at the operational impacts of those areas. So for The training aspects, for example, for what you need to be able to do to land a vehicle on the lunar surface. There are folks that are looking very critically at what are those skills that we need to have training address and what types of platforms we need. And so even before the providers are ready to do that, people at NASA are looking at raising up those capabilities so that we can provide some generic training that would be helpful no matter what provider is coming up with the vehicle or what they're asking the crews to do. But then also having a platform that then the commercial providers can also take advantage of to provide the more mission-specific training that we need the crews to have for their vehicle.
It's not just NASA astronauts that will feel the effects of the environment. The private astronauts would too.
And
they're also
and
human.
we'll have different providers, so we'll need to have a platform that different providers can be able to leverage to provide that training.
What's next for neuroscientists at NASA? What other areas related to this are you guys working on or think ought to be worked on?
Well, there are several that will probably never happen.
Oh.
Artificial gravity in flight.
Right.
I think would be probably one of the biggest steps we could take. Making that happen is probably going to be very, very difficult. In the past, there have been several designs. None of it seems to be ever going to be implemented, however.
Because it's not feasible, or it's not
it's feasible.
Too expensive, or?
It's feasible. It's probably very expensive.
Okay.
But maintaining a relationship to a gravitational field other than total microgravity is probably one of the best things we could do. Depends on the kind of ship you have. What we're talking about now in terms of the vehicles in design and in use. There's no way to really provide any kind of artificial gravity in flight.
Does it involve rotation of the vehicle?
It involves rotation of the vehicle, and it has several problems that sort of trickle down through all the other sciences. If you provide rotation of the entire spacecraft, you're going to upset a lot of people. People that have experiments that require almost a total vibration-free environment.
Right.
It's going to vibrate. There's no doubt about it. And having a vibrating or non-vibrating environment requires a vehicle that can maybe separate, and where you can have a daily dose of artificial gravity. There are other problems associated with artificial gravity, and that is the vestibular system doesn't really appreciate being exposed to cross-coupled angular accelerations.
Cross what kind?
Cross-coupled.
Cross-coupled angular accelerations, okay.
Yeah. So making the environment such that you can minimize that is going to require less movement on the part of the person. Hopefully you'll be able to walk and run. Skylab was
thinking of the same thing.
Good example. The upper deck was fairly empty. It had water containers around the vehicle, and crew members had started running on those water containers. Big circle. Yeah, they did very well. Yeah, so it's certainly feasible.
But it's all very interesting to think about when you get people who are smart enough to know the actual details of the things that have to be considered in order to make the whole thing work. It's just fascinating.
Yeah, it all sort of filters down.
Mill Reschke and Scott Wood, I appreciate your taking the time to talk about this. I love it. It was great.
Thank you very much for having us.
Thank you.
Houston, go ahead.
Stop of the space shuttle.
Roger, 0J, and I feel
Shuttle has cleared the tower.
Became a theme for all mankind.
It's actually a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Never Houston, welcome to space.
Before the first people ever left this planet on top of a rocket, the scientific concerns about how the space environment might impact those people were very broad ones, like will they be able to breathe or swallow? Will they be able to do any work? Could they survive the radiation? Well, over the years, scientists have learned so much about how the lack of gravity and the other characteristics of the space environment impact the operation of this human machine, and about how the body and mind react to the changing conditions in the short term while filing away data on the experience to be ready to respond when the circumstances return. The work of those researchers, men and women like Scott Wood and Mill Reschke, will be crucial to our eventual success in putting people on the Moon and Mars for longer periods of time to explore those new horizons. I want to remind you that you can go online to keep up with all things NASA at nasa.gov. In fact, you can get all the NASA news you want delivered to you every week. Just go to nasa.gov/subscribe to sign up for the NASA newsletter. You can find the full category of all our podcast episodes by going to nasa.gov/podcasts and scrolling to our name. You can find all the other NASA podcasts right there at the same spot where you can find us, nasa.gov/podcasts. Very convenient. This episode was recorded on August 19th, 2022. Thanks to Will Flato, Gary Jordan, Heidi Lavelle, Belinda Polito, and Jaden Jennings for their help with the production, and Scott Wood and Mill Reschke for helping us understand the issue and what's being done to address it. We'll be back next week.
Houston, we have a podcast. Welcome to the official podcast of the NASA Johnson Space Center, episode 260, Mysteries of Dust. I'm Gary Jordan, and I'll be your host today. On this podcast, we bring in the experts, scientists, engineers, and astronauts, all to let you know what's going on in the world of human spaceflight. Dust is really everywhere on Earth. In our own lives, we may think of hazy skies that eventually just go away, but these tiny particles can have a big impact on the planet's climate. One experiment that launched to the International Space Station on SpaceX's 25th cargo resupply mission is taking a whole new look at earthly dust. The Earth Surface Mineral Dust Source Investigation, or EMIT, is making history by studying the composition of surface mineral dusts around the entire world. Joining us from NASA's Jet Propulsion Laboratory to talk about EMIT, we have Dr. Robert Green and Dr. David Thompson. Robert Green is the principal investigator of EMIT. For more than 25 years, his research has used advanced imaging spectrometer instrumentation to test hypotheses and pursue scientific investigations and applications research on Earth and throughout the solar system. David Thompson is a senior research scientist at the Jet Propulsion Laboratory and the California Institute of Technology. His research advances the algorithms and practice of imaging spectroscopy for characterizing Earth and other planetary bodies. He's an instrument scientist for NASA's EMIT and has a long history on the programming end of spectroscopy. David's technologies have been fielded in 4 continents, 3 oceans, 3 Earth-orbiting spacecraft, and twice to the surface of Mars. Rob and David will clear the dust off the mysteries of EMIT and reveal how we'll soon be able to better understand more about our home planet. Here we go. Enjoy.
T-minus 5 seconds and counting. Mark. Mission start. T0 launch commit lights are correct.
There she goes.
Houston, we have a podcast.
Rob and David, thank you so much for coming on Houston. We have a podcast.
Hello, this is Rob Green. I'm very pleased to join you today.
And this is David Thompson. It's a pleasure to be here.
Great. This is such an interesting experiment. There's a lot of stuff going on in the International Space Station, but this one is looking at the Earth in a very unique way. And I just wanted to start, I think, before we really get into the experiment with a little bit about yourselves, because this is a very interesting area of study. It seems very specific, and I wonder just sort of what led you to it. Rob, if we can start with you, just sort of how your career sort of led you to studying, of all things, dust on the surface of Earth.
Sure. Glad to chat about that. It goes back actually to my master's degree at Stanford University, where I got very interested in spectroscopy of the Earth system. It was just becoming a field that was being applied with a new set of instruments called imaging spectrometers. And that actually drew me to JPL to work with the very first imaging spectrometer and a follow-on spectrometer. And it turns out a series of spectrometers that we've used to answer questions on Earth and across the solar system. But specifically on EMIT, it was realizing we had this experimental technology of imaging spectroscopy, and talking with my colleagues at the USGS, realizing there is this gap in knowledge about the mineral source regions that when encountering high winds, those minerals are emitted or launched into the atmosphere, where they interact throughout the Earth system, and realizing there was a gap in knowledge of what the source region mineralogy were, and that if we could get at that, we could really address a suite of science questions, and specifically the ones that EMIT tackles, which is related to climate direct radiative forcing, heating, cooling of our planet locally, globally, and regionally.
Mm. So, I mean, what was originally that drew you to EMIT specifically and to this area of study? You know, there's a lot of different things that are affecting the climate. You know, you could talk about CO2 emissions. You can talk about a lot of different things, but this one seems very specific. Was it sort of a mix of maybe the mineralogy, geology, and then earth science that sort of drew you to this world that you found most fascinating, or maybe a gap in the knowledge that you just wanted to explore?
Yes, I'm an earth scientist, experimentalist by nature, and have been involved with a range of studies across the Earth system. So it was realization that here was an opportunity to test a hypothesis to advance science with the technology and the experimental method that I've specialized in, which is imaging spectroscopy. And they came together perfectly. There's a huge gap in knowledge. Currently, the Earth's mineral dust source regions are characterized by only 5,000 mineral analyses for the entire planet Earth. And we had an opportunity with NASA technology from the International Space Station to update that with 1 billion direct observations of the surface mineralogy via imaging spectroscopy. So once that narrative and opportunity to test hypotheses and move science forward became clear, that's when we pulled the science team together and we wrote this compelling proposal, which was reviewed in a competitive sense and selected to be implemented.
Excellent. I want to dive into that as well, too, a little later in this podcast, just how EMIT came to be. But David, we'll go to you for a second, too, because I want to understand a little bit about what led you to this world, and then ultimately how your worlds collided with you and Rob to eventually start studying this.
Sure. Well, I came to this world by a rather circuitous route, actually. I started off in the field of machine learning and artificial intelligence, doing data science-related things. Throughout grad school in Carnegie Mellon, I studied robotics, mostly in the context of planetary exploration. And in that domain, you really can't escape spectrometers. They're everywhere. These are the instruments that are really fundamental for understanding the composition of planetary bodies. If you're rolling over the surface of Mars with a rover or looking at distant exoplanets, everything is a spectrometer practically. And so I became acquainted with this technique pretty early. But it was always from a data science perspective, always from trying to interpret the data, look at patterns in the data, and understand from a mathematical perspective how we can make these measurements accurately. And then when I came to JPL, everybody started talking to me about imaging spectroscopy, for which JPL at that time and currently is still very famous for. JPL originated the technique early in the 80s, and since then has really refined and perfected it. And so I was introduced to these fantastic new data sets where now I just wasn't looking at a single spectrum. I had a whole image where every pixel in the image was a full spectrum of data. And these are just incredibly rich, powerful objects, almost magical in their power for understanding the world around us. And so I became enamored with them and came to meet Rob, who at that point was spearheading JPL imaging spectroscopy development, and came to the EMIT mission through that. So since then, I've been working on advancing the measurement technique, bringing to bear all of these tools of statistics and computer science on these really rich, fantastic data sets, and have added to that the physics understanding, I think, that is so critical for interpreting these data.
Very interesting. Now, imaging spectrometers, this is something that I want to focus on for just a little bit. You talked about these opening up a whole new world, and I want to understand, Robert, maybe we'll go to you for a little bit, is just, it's a world of looking at things, all of these different aspects of science, just in a different way. So when it came to this mineral dust and that sort of thing, and really just some of your other work as well, we can even dive into a little bit of your other work. When you started applying this imaging spectrometers to and studying some of these things in your career, what was, I think, maybe the most fascinating or the most surprising in terms of what they revealed and the stories that they told that was maybe promised in some of the early uses of this technology?
Sure. Pleased to. It is one of my passions. I would say spectroscopy is one of the most important exploratory methods discovered by humanity. And again, it goes back to Fraunhofer in Germany, who used a spectrometer to answer some questions. But what we do when we measure a spectrum of reflected light, which is the area I'll be speaking about, is we measure the light that's interacted with matter in some sense. In this case of EMIT, we look at light that's originated from the sun, it's passed through the Earth's atmosphere, it's interacted with minerals and other materials on the surface and up to our instrument. And we measure that light, and we notice that the light we measure is different than the light that left the sun. And it's different because the fingerprints of the molecules and particles it's interacted with have taken bits and pieces, in some cases added bits and pieces to the spectrum we got to measure. And then we can look at the spectrum we measured and invert or derive those materials. We have to derive the atmosphere and compensate for it. If there's vegetation, we have to assess it and remove it. And then we get to the mineral signatures, and there we see the signatures of the mineral molecules on the surface. So it's an incredibly powerful technique. And that's the core, is we're looking at the fingerprints of matter that has interacted with that light signal that we got to measure. And just briefly, I've seen it shift paradigms again and again. I was involved with the Moon Mineralogy Mapper, which was launched in 2008. And a year and a day after launch, we had the cover of the journal Science with the discovery of hydroxyl and water compounds on the illuminated surface of the moon, which was thought not to be possible that the moon gets up to 400 Kelvin. Just an example that we captured the spectrum that included the signature region of hydroxyl and water, and we saw it in places no one expected. That was extraordinary. Another quick one on our planet is methane. We deal with comparatively coarse spectral resolution imaging spectrometers, 5 and 10 nanometers. The conventional wisdom, you would never be able to look at gases in the Earth's atmosphere in any useful way with these measurements. But we did. We overflew gas fields, petroleum extraction fields in California, and methane seeps in the Santa Barbara Channel. And we were very sensitive, in fact, to point source emissions where the concentrations are high. And now JPL is building an instrument called the Carbon Plume Mapper for space to map methane point sources and help us mitigate that. So those are two examples: water on the moon, methane point sources, which the conventional wisdom was this, what's going to be possible with the kind of spectroscopy we were using, and yet we've shown that, in fact, it is possible, and it's incredibly powerful. So those are just a couple of examples.
Very powerful examples, too. What you're talking about is using this technology to look at something just in a new way. And I think the idea is you just take that technology and you look at it with the expectation that you might be surprised, that you might find something there that that you didn't really expect, or maybe even know to look for, or maybe, and Rob, you can maybe help clarify this, is did you maybe have an idea of what you were looking for while looking for it, or was it really just, let's see what we find?
We did have an idea in both cases. For the moon, we thought we might see evidence of hydroxyl up near the permanently shadowed regions. Just a fleeting example. There are permanently shadowed craters on the moon where the hypothesis that the sun never gets into them. If you were going to have water or ice, that's where it would be. So we knew we should be looking. But we found is the hydroxyl signature extends to tremendously low latitudes, almost to the equator, perhaps, of the moon. And that was completely unexpected. And in the case of methane, we knew methane was a molecule interacting in our spectrum and its signature would be there. But the conventional wisdom is you needed a much finer spectral resolution. And you do to get to lower precisions. But we discovered that the point sources, the place where the methane is coming out of the gas pipeline leak or whatever, that in a localized region, the concentrations are high enough for us to have really wonderful sensitivity to map these point sources. And it's those, quote, super emitters that if we can get a handle on now and mitigate, we can actually turn some tenths of a C off the current trend in global temperature rise. Now, we've diverged far from emit, but that's a quick answer.
But the idea, we're sort of giving an understanding of what the technology is inside emit and why it's important. And we'll investigate that a little further. But that's what's being revealed to me, doing this deeper dive into spectroscopy. And David, I think when you talked about your early fascination with it, it seems to me that that's really it, is looking at things a little bit differently and finding these, and maybe coming up with a hypothesis ahead of time, like Rob was mentioning, but maybe finding some things. And I think maybe I'm trying to feel that sense of excitement that maybe you feel, and I think what I can maybe relate to more so is if you're parsing through these data and you see, and you're seeing this new way of looking at something through spectroscopy, and you have that moment where something is revealed to you, the thing that you were looking for, or maybe the thing that you were not looking for. Can you talk about maybe you have some story of parsing through data on one of your earlier experiments where you found something, and that emotion that came to surface while you were looking at just pieces of data, but just through this new lens?
Oh, yeah, no, absolutely. I think, well, I should say first that I think both of Rob's examples, methane and water on the moon, sort of exemplify the nature of imaging spectroscopy and these really rich data sets where even a single image can be the subject of its own investigation. And you can continue studying that image for years and discovering new things about it that you didn't know before just because of the richness of that data. We're measuring a wavelength regime from the ultraviolet out through the shortwave infrared. So we're capturing most of the sun's energy, the incident on the surface that's reflected back to the sensor and available to it. And in that wavelength range, we're sensitive to hundreds, thousands of different physical and chemical processes on the Earth's surface and in the atmosphere, all of which leave these distinctive fingerprints and modulations on the spectra that we receive. So even in a single spectrum, a few hundred numbers worth of illumination values at the sensor, that's the potential for a year of exploration to try and model and understand all the processes that gave rise to that single measurement. Now, that's just one pixel of a single image that we acquire. So now it gives you a feel for just how rich these data sets are and how many different processes we're sensitive to. And I think for me, this was driven home in, I'll talk actually about the methane case that Rob was describing. So for a while, we had studied methane exclusively in images after the fact, but it was thought that by actually loading this software onto the aircraft itself as we were flying over these methane fields, we could be a little bit more dynamic in our mission planning. So we could actually fly over a field, identify the specific plumes and the facilities that were leaking, and then quickly text a ground team that could go out with a separate instrument to corroborate that measurement and give us for the first time a real ground truth validation of these remote measurements that we were making. And so this involved actually me flying around in an aircraft, debugging software on the sensor in real time while we were trying to get the thing to run. This happened for a few weeks while we did test flights. And then finally, game day came. We flew out to Four Corners, New Mexico, where we'd identified a large-scale methane hotspot from space. But the sensor could only tell us that it was in the approximate vicinity of Four Corners. It couldn't actually identify whether it was coming from an anthropogenic source or a geologic seep or anything like that. So through this campaign, we overflew a couple of coal mines, turned on the sensor, and immediately saw these beautiful methane plumes streaming across the scene as we were flying overhead. And we didn't even know if it would work or not, until we tried it. But there you go. And immediately we were able to text the ground team to go out with a thermal camera and see the plumes from the ground and confirm that, yes, indeed, these detections that we were making were very real. And so this is just one of many examples where, imaging spectroscopy surprised us with its power.
Amazing. What a moment. I want to take that and what we're learning about spectroscopy and its importance and sort of fold that into this new topic, which would be more so on the dust. Now, we're going to talk about emit, and what we're looking at is dust. And from understanding, just talking to you gentlemen a little bit ahead of this, it's a very particular thing that we're looking at when it comes to dust. Rob, if you can just sort of give us an overview of what it is exactly this area of studying dust on the planet. There's dust everywhere. It's blowing all over the place. So if you can give us an understanding of why this is being studied, what its impact is on the planet, and then we'll fold into exactly what it is emit is looking at.
Okay, terrific. So in airland regions of our planet, under conditions of high winds, surface mineral dust, the little particles left over from rocks being ground up through various alluvial processes typically, are launched into the atmosphere. And then when they enter the atmosphere, they begin to interact immediately. They absorb or scatter light, which heats or cools the atmosphere in that region. They play a role in cloud formation, the condensation nuclei. They actually change the chemistry of the atmosphere, which enables other atmospheric processes. So right off, surface connected to atmosphere. Then as they're deposited, if they're deposited in oceans, they become nutrients and can cause algal blooms affecting aquatic ecosystems. If they deposited in terrestrial ecosystems, in rainforests, for example, of South America, they can be key nutrients there as well, playing a role in those ecosystems. If those dust particles land on snow, they accelerate melting, and that has huge impacts for local albedos, brightness or darknesses of the surface, but maybe as importantly, water resources, how fast that snowpack melts in California, where I live, has a big impact on how much water comes from the Sierra Nevadas that society can use or not use. The same is true for Colorado and many other parts of the world that rely on that. And then if they land where we live, they can be a visibility hazard. There can be all sorts of consequences to visibility. And in fact, their particulate nature and chemical composition, a la mineralogy, can have a toxicity impact. For example, there are dust regions in California where the dust particles are made of naturally occurring asbestos, which you could imagine would be a bad thing to breathe. So those are so the mineral dust cycle is throughout the Earth system. It connects the surface geology to the atmosphere, to the solar energy absorbed, to the aquatic ecosystem, to the terrestrial ecosystem, to the snow hydrology, and to the area that humanity lives. So it's just the most extraordinary cycle, and then we discovered there was a gap in knowledge. People don't understand what the composition of the source regions are.
So what does that mean then? So we have this, you're talking about a greater understanding of what's happening and how dust is affecting, you talked about how dust, affects certain ecosystem, how it travels, but what exactly was that lack of knowledge that maybe you needed to investigate? What would that reveal to you?
Okay, so the other thing that's going on in the scientific community, there are these spectacular Earth system models. These are models that attempt to model the entire Earth system that you can then run forward and backward. You know, if CO2 changes, if methane changes, all sorts of things to assess what's happening now on our planet and what the certainty of that is. These get folded into the IPCC, for example, and to look into the future, what might happen under various scenarios. So the dust cycle is part of that, as it must be, given all the parts of the Earth system it interacts with. We discovered in early conversations when thinking about this with our colleagues who are Earth system modelers, Natalie Mahawold, Ron Miller, Paul Jeannot, that the current Earth system models use a database that is traced to simply 5,000 mineral analyses, where the minerals have been collected from a location on planet Earth and analyzed for what minerals are there. Then they've used various interpolation methods to take those 5,000 samples and make estimates of what the mineralogy is for the entire surface of planet Earth. That's a big leap, 5,000 to the entire surface of the Earth. They're not even sampled uniformly. So we realized, and then those models weren't giving the predictions that were expected. So that was evidence that the models weren't validated. They weren't doing as well as they needed to pursue the science questions that wanted to be pursued. So that was the germ of the idea that we could address this, and we could address this hugely by going from, again, 5,000 to a state where we could have 1 billion direct observations of uniformly of the arid land regions of our planet. And that is the focus of the mission. And also it's focused very much on the direct radiator forcing effect affecting climate, even though our data we expect to be used for a wide range of other science objectives.
So, David, you're presented with this big problem when it comes to gathering data, and you have to design an instrument, and the challenge is, hey, we only have 5,000 samples. We need to have a lot more than that. How are we going to cover a lot of ground? So can you tell us about the story of this idea of where do we put the imaging spectroscopy, and then how the International Space Station eventually came up as a good place for that?
Sure. Well, of course, if you want to cover a lot of terrain on planet Earth, the easiest way to do that is from orbit. And a variety of different orbits that you can use. Some are more challenging to reach than others, but it turns out that the International Space Station was a perfect match for the EMIT objectives. And the reason is that most of these dust-forming regions are arid, mid-latitude regions. That is, they concentrate around the equator. And the ISS, with its inclined orbit, also covers this area of the globe. So it passes over these mid-latitude regions. And in fact, we discovered that based on our best estimates of where the mineral dust was coming from, we would be able to overfly all of those regions from the ISS. And of course, the ISS has lots of other advantages as a platform. It provides power, provides data, and this really was a perfect match. So the instrument was originally designed in order to plug into the ISS and take advantage of these resources. And in turn, of course, we'd be downlinking data through the International Space Station, all of that existing infrastructure that would let us command the instrument more effectively and then recover the data.
So what sorts of things did you work on that eventually led you to? You talked. It was Robert actually that mentioned submitting a proposal about here's our idea for we're going to put this thing on the International Space Station. Talk about some of the work that you've done before that eventually led to the success of accepting the proposal, from your design of the instrumentation to the confidence that NASA had that you could put it on the International Space Station and this would work, and that your objectives and your goals were sound and that sort of thing. Talk about the approach that eventually led you to confidence in submitting to NASA and them saying yes.
Yeah, and it began far before our first proposal to the Earth Venture Instrument Program, which is the instrument program that ultimately funded EMIT to go to the space station. By the time we wrote the proposal, imaging spectroscopy was a mature technology. It had been tested many times before on a variety of different airborne platforms. And this is pretty typical of NASA instruments. Before you are able to put it into space, you first have to demonstrate using some proxy that you can do reasonable remote sensing. So there's a long history of campaigns for mineralogy and many other objectives as well, using imaging spectrometers developed at JPL that flew on a variety of different platforms. The high-altitude ER-2 aircraft that NASA flies flew back and forth across California for many years, actually, doing geology and many other investigations as well. And we've worked with a variety of partners. The USGS for a long time has been our boots on the ground doing mineral validation campaigns and then using these geologic data for their own purposes. And so there's a long history of publication record, both in the journal literature and various conferences, that imaging spectroscopy worked for studying the Earth's surface and for minerals on the planet. And so we had good confidence. The algorithms were mature, and we'd had demonstrated that before we wrote the first proposal. And it didn't go in the first time, actually. We wrote a proposal a couple of years before, and it was actually selected. So as with all of these things, it takes time and refinement to make the ideas better and more precise. And the instrument evolved too. So initially, after selection, we had the concept that there would be a mirror that would allow us to point around at different targets. It was determined that it was more efficient to just maintain a nadir-pointed perspective and that we'd be able to cover the entire terrain that we wanted to using that much simpler instrument. So the instrument design evolved as well, even after selection. But we were left now, today, in 2022, with quite a capable instrument, actually. And the first initial data that we're getting is really quite promising. So it's living up to our expectations as far as making these accurate measurements from space.
Interesting. Yeah, let's dive into the design just a tad more, David. You talked about a couple different approaches to how exactly you're going to get this imaging spectrometer on the International Space Station, and eventually there was one that met your needs. And you talked about a significant level of confidence in the instrument. Can you talk about just its design and how you get? You talked about you have some interesting areas of study that EMIT needs to look at, and you mentioned it gets to look at all of them. So how exactly is the design of EMIT that allows you to do that?
Yeah, well, there are a couple of different parameters that we need to consider in designing an instrument to meet these science objectives. So we start with a target, which is mineralogy on the surface. We want to be able to measure the distinct mineral absorption features to a given level of precision, because we decided as a science team that this is the accuracy we need, a 2% change in the relative depth of an absorption feature in order to significantly advance our understanding for these Earth system models. So we began with this target, and then from there we could discern what kind of spectrometer we would need to build in terms of the signal-to-noise ratio that would be required. That is the sensitivity to subtle changes in surface reflectance that we would need to be able to measure. And so that gives us the approximate dimensions of the spectrometer and the optical layout, the kind of detector we would need, for instance. We knew that we needed to measure the wavelength range out into the shortwave infrared, because many of the minerals that we were interested in have distinctive, unique signatures in that wavelength range. So that necessitated a cryogenic system that would be able to cool the detector cold enough that we would be able to measure those longer wavelengths. And then, of course, another dimension of the design that we worked on was the coverage that I alluded to before. So in order to cover all of these dust-forming regions of the world, we need a perspective, that is the ISS orbit, and we need an instrument with a swath wide enough that we can collect enough data with each pass to ensure that that area is covered in a reasonable amount of time. And reasonable in our case was a year of operations, and we hope to be able to cover the key mineral dust-forming areas of the Earth long before that year is up.
Very good. Okay, so obviously it took a lot of work to get to that point. Did you, by chance, get to actually go to the launch and see all of your hard work and this thing that you've been dedicating so much time to actually leave the planet and head towards the space station?
Yep, indeed. The entire team went down to see the launch. A couple of times, actually. The launch was initially delayed due to a challenge they had with the launch vehicle, but that was remedied. And in the end, we all got to see it launch on Bastille Day this year. It was absolutely spectacular. A twilight launch, the setting sun illuminating the rocket plume as it launched off into space. We could see the exhaust illuminated, and it was truly spectacular. Of course, it was a little hair-raising as well, because that was our baby on top of that rocket, that we'd spent years developing and refining, and there it was on top of a controlled bomb. But all's well, and we arrived at the space station and were successfully installed. So it just went as smoothly as could be asked.
Yeah, it was in the unpressurized trunk of SpaceX, right? That's where it was?
That's right. Yep.
Okay, so it had to be removed. Now, Rob, talk about the process of removing this thing from the trunk, getting it installed, and that emotion that you felt whenever you started seeing the data come through. This thing was up and running. The science was beginning.
Yes, it was quite a remarkable process, and that's again one of the joys of the International Space Station. There are wonderful steps along the way from launch to when you get plugged in, turned on, and get first light. More steps than you have in a typical mission, maybe to Mars or to the Moon, for example. So I thoroughly enjoyed that. So again, we arrived at the space station in the trunks safely. That was step one. Then we wanted to wait until the solar beta angle, which is a description of how the sun would land on emit when it was being transferred from the trunk to its site, was in a favorable regime. So we paused for a few days there. Survival heaters, emit was safe in the trunk. Then the conditions became right, and we were all glued to the internet, watching the arm reach back, grab emit, and then ever so slowly, I think this took about 60 hours, move deliberately, carefully planned, exquisitely planned to its installation site. Along the way, we had to pause again for the night and people to take a break. And so we connected another grapple to emit to provide extra power to make sure it was warm. So there was a double grapple period while we waited for that to happen. There are beautiful pictures of emit above the Earth in this pause. Then we continued from that site the next morning to be installed, and we watched ourselves get loaded into the ELC Site 8, ELC1 Site 8, and then ratcheted in, and then we got very quick feedback when it was powered on that, yes, we were seeing telemetry, we were seeing power, and we were seeing high rate data, and we would see that we could command it. So that was just amazing. Those are the things you got to have. If any of those aren't true, there's a problem, Houston. And so then we had to do the next steps, a little bit of decontamination, drive off any water that might be there that would frost up our cryo cooler when it was turned on. So we waited a little while with heaters on to drive away the water, finish that. Then we had to take the next major step, which is take our instrument cold. It has to get down. The detector wants to get down to 160 Kelvin for us to see those wavelengths in the 2.5 or the shortwave infrared region. So we knew it was cold, and then we said, okay, where's our first chance for illumination? And it turns out it was in Western Australia. And so we knew the instrument was commanded to collect those data sets and subsequent ones. We had to wait. We knew that the data were collected. They're stored on the ISS. They have to come down to Huntsville and then moved over to JPL. And so I guess it was probably about 10 o'clock in the morning the next day. The first data were collected on the 28th of July. That we saw the first raw data sets, and they were exactly what I'd hoped. We had the image and we had the spectrum, and all the spectrum was there with all the fingerprints of the Earth system, the ones we could easily see, which tend to be dominated by the atmosphere to first order, but even vegetation. So again, there was a tear in my eye that this was the culmination for me of more than 30 years, not just emit, but the preceding years in this field of imaging spectroscopy, and the honor to lead this effort to get this class of instrument looking at our planet for this important science and the other science it can enable.
What an emotional time. Yeah, I mean, I was with you just on the emotion of for me, I don't know how you were, but as you were describing the 60 hours of this slow and careful maneuver of this very precious cargo, just hoping that everything went smoothly until it was installed. I mean, I was thinking about like 60 hours of basically white knuckling it. I don't know how you felt, but this is your precious hardware that's floating through space. And you mentioned like cool pictures and stuff, but how was that? Was it a tense 60 hours or was it very focused 60 hours?
The competence of the teams that run the ISS and run the ARM are so extraordinary that I really wasn't concerned that I was just reveling in it, and I continue to as it sends the data down. So again, there's important touchstones? Absolutely. If something isn't what you expect, that's an issue. This team, the team, JPL and the ISS team will work the issue. And I had just this incredible confidence. So again, I wasn't so concerned, but I was aware of what we were going through. The things needed to work right. I was pleased every step along the way. But boy, the team that built Emit and the team that had taken care of it, including SpaceX, getting it up there, is just magnificent. So again, maybe I wouldn't say I was foolish, but I'm an optimistic guy too. So I was always optimistic, but realizing, things don't always go well, but we had the teams to address any glitches. And I won't say that there was a couple glitches along the way, but the team just focused on it and solved them. We built an instrument that has some resiliency as well. So I was just thrilled when each checkpoint was cleared. And in fact, we cleared almost all of them a little ahead of schedule, which was, again, further evidence of the teams that are involved in this process.
Wow.
Their excellence.
Well, I'm glad to be talking to you so soon after you started getting your that data from the first set of data from Western Australia. This is only a couple of weeks after that. You said, I think it was July 28th. So talk about you said you had a tear come to your eye, you wiped it away, and it seems like it was time to buckle down and really get to the science and the measurements. And from what you alluded to in the beginning of our conversation here, it's you've been doing a lot over these past couple of weeks.
Yeah, I want to hand it off to David because he has many contributions, but the algorithms that take these raw data, which I can look at, and I used to be able to write code that could process, he developed the algorithm. So he can talk maybe a little bit about what we quickly did with that first flight data, which are raw data. It's unprecedented to go raw data to higher level products in hours and have them, I will argue, look as good as they did, that we could have the release with NASA and elsewhere of the first light Emit image cube and radiant spectra. But I guess I would love David to speak about a little bit more about that.
Oh, absolutely. Please take it away, David.
Yes. He was at the heart of it.
Sure. Well, just to set the stage, so Emit operations, it actually begins with a period, even before operations, there's a period called on-orbit checkout, or IOC, and this will last about maybe a month after the installation, after Emit is initially turned on and starts collecting data. So this is our time to take our own calibration measurements from space, to check out the instrument in all its different capacities, to make sure that we're ready to begin the formal operations that will result in our science objectives being met. So this is our time now, as we're speaking today, to test out the instrument and make sure that it's functioning as we intended. And it really begins with a stable instrument. So and JPL for a long time has been maturing the technologies of building an instrument that's stable, that's spectrally uniform, meaning it's accurate across the entire field of view of the instrument, that it produces good, accurate spectra. So if you don't have that, then all of the subsequent analyses are for naught, right? And we verified this in the laboratory. When we still had Emit here at the laboratory, we would measure it by shining controlled stimulus into the instrument and then seeing how that hit the focal plane array, seeing the signals that the instrument would produce, to build up models of how the instrument responded to incoming illumination. And this is called the calibration process. So we would figure out what's called a wavelength calibration, so what specific wavelength each channel of the instrument was sensitive to, and then a radiometric calibration, how the focal plane array responded to light, how sensitive it was to photons. And so these different aspects of calibration were rough drafted during our laboratory measurements, and then we let the instrument go. And there was a period where it sat in storage, where it was launched on a rocket, where it was floated through space. And the question on our minds when it was first turned on was, would the instrument have shifted? Would our initial laboratory measurements hold? And so, as Rob said, when we first got our first light image and we saw a beautiful radiant spectrum, it was immediately apparent that, yes, the instrument was completely stable, that it was more or less exactly as we had measured it in our laboratory. And that's really what allowed us to produce those early products as quickly as we did, because the instrument was solid and because the measurements that we made before could be carried along. Now, of course, we'll be making refinements. And so the next couple of weeks will involve looking at different objects on the surface of the Earth where we know a little bit about what we should be seeing, so that we can make adjustments in our calibration to refine our understanding of how the instrument's responding now that it's on the space station. And so this process will continue. We'll be refining the methods by which we produce what's called the radiant spectrum, which is our measurement of illumination at the sensor. And then Rob alluded to the process by which that measurement is then analyzed in order to infer properties of the Earth's surface. So we need to use that radiance, the incident illumination at the aperture, to estimate what the atmospheric state is, because we're sensitive to all of that. As we discussed earlier in the methane conversation, all of the different constituencies of the atmosphere leave their fingerprints on that spectrum, so we need to account for that as well. And that's what gives us our measurement of the surface reflectance, but roughly speaking, the fraction of incident illumination of the surface that's reflected back towards the sensor. And that's where all of our interesting mineral features live. So the next subsequent stage of analysis after that is to look at the surface reflectance spectrum to figure out the abundance of various minerals that are on the surface within that pixel that EMIT is measuring. And that's what allows us to create the mineral maps that will ultimately feed the Earth system models and give them updated estimates of surface mineralogy.
And how long? This is going to be a pretty lengthy process, I assume, right? You're going to have to once you get to that point where you have that confidence in your instrumentation that you know you're going to be getting some really good data, and you can have confidence in your instrument. How long is the process of actually measuring of day in, day out operations and generating those maps?
Yeah, well, I expect I should say, actually, we already have pretty good confidence that EMIT is well calibrated and is producing accurate data. There are always refinements that one can make. It's kind of like tuning an instrument, right? And you want to keep updating it over time for every subtle shift, because we're very sensitive to even very, very tiny, micron level shifts in the focal plane array over time. So we'll be tracking that very closely, but it already looks very good. And then, of course, EMIT will start the process of science operations, measuring Earth's mineral dust forming regions whenever the ISS flies over. And that's slated to take probably, several months actually, anywhere from 4 to 6 months, depending on cloud cover, in order to cover the entire dust forming regions of the globe, at least once everywhere that we care about. Obviously, we can't see through clouds, so that's really the unknown in the equation. How many clouds will we encounter? But whenever there's a clear sky, we'll be able to map that mineralogy, and we'll have that in the bag thereafter. So that's really what dictates how long it will take to finish the measurements.
And then anything after is just sort of a nice to have, right? Because 6 months, it's not like you're going to be flicking the switch on the off button quite. If you have the chance to continue to gather data and maybe fill in some of those gaps just in case there's too much cloud coverage, like I'm assuming you can just keep going.
Absolutely. We'll want to continue refining our measurements, validating measurements of places that we've already observed. There are a variety of different other objectives that other scientists might choose to pursue using the EMIT data. So I'm hoping that they can continue to use EMIT data products after our key mission objectives have been achieved. That's obviously outside the purview of our own project, but EMIT will be good for a lot of other things besides mineral dust.
So as all of your hard work, David, on the instrument, right? I asked, your level of confidence in the instrument, and you said, "Oh, we're pretty confident in the instrument." But I wonder, is it because you had that sigh of relief whenever you actually did the initial checkouts, the on-orbit checkouts, and it was as you expected? So I'm assuming you have had that sigh of relief of, all right, it's working, we did it. But it's at this point you just mentioned, just a couple of tweaks and refinements as you would normally do. But seems like you've gotten past what I assume to you and your role in this investigation is probably one of the more stressful events.
Yeah, we're certainly over the threshold where we can say that EMIT is functioning as advertised, and we'll be able to make those final tune-ups and get it working to perfect. We're all kind of perfectionists here, so we want to make sure that the data is accurate as possible. Fortunately, the planet is given us all these beautiful calibration objects. The atmosphere, with its gas absorption features, gives us known wavelength positions of these features that we can calibrate against. And there are other parts of the surface that we can use to calibrate other aspects of the system. So we'll continue to use this physics knowledge of what we should be seeing in the atmosphere and on the surface to tweak our calibration as we go. But we've started with a very stable instrument, so I don't expect to have to update very much over the course of the mission.
Very good. Now, Robert, as a principal investigator for this, I'm assuming you're going into this with maybe some expectations, maybe some hopes. As you're going into the operations, actually starting to gather data and cover the whole area of Earth that is part of your objective. That is, you really this instrument is able to fill in the gaps of what David mentioned is really everywhere you want to cover. So, as a principal investigator going into these next couple of months of data gathering, what are your hopes? What are your ambitions? What are your hypotheses of what you expect and anticipate from this experiment?
Yeah, I'm just so excited to begin to look at the mineral maps that we produce and peel back this unknown of what is there, what's coming off the Sahel, Southern Sudan, other parts of Africa and Australia, South America, United States. What are those source regions? And then working closely with my colleagues on the science team who are running the Earth system models and starting to work our measurements in to close that gap and to increase the fidelity of the output. I'm just so excited. Every image that comes down is just spectacular. Even ones with clouds. Oh, that's clouds. That's amazing. Look at those signatures. David has done some work on understanding whether clouds are liquid water or ice. That's revealed in the spectroscopy. Well, that's not the focus of EMIT. We do get cloud images, so we can look at that. But again, the surface mineralogy, the nature of this magical planet we live on, and in this case, what minerals are at the surface and how are they likely to be in play as they get blown into the atmosphere and interact throughout the Earth system. That's what I'm looking forward to. Every day I get up, we have meetings every day on what's going on with EMIT, what data, David and another colleague, Phil Roderick, almost always have something to show about what we've seen in the latest data sets coming down as we're in this early phase, and it's incredibly exciting.
Do you think that these data that you're gathering, you talked about filling in the gaps of knowledge of surface mineralogy and exactly what you're looking at? You're getting a lot of data across the whole Earth, and I wonder, you may have some hypotheses going into it on how that can contribute to our overall understanding of the planet and climate science and all of these different things. But do you think there's a chance that maybe these data can be available to other scientists so that they can maybe take that and run with some idea that maybe we haven't even thought of yet? Do you think that what EMIT is doing is going to contribute to a greater understanding of our planet in ways maybe we haven't even expected yet?
Absolutely. This will be the first data set of its class and its kind for our planet. Now, we're not wall to wall, but we're getting a big chunk of the planet with the highest quality spectra that have ever been measured. And that's a benchmark. Our planet is changing. So the sooner we get that data set, the better. Another point, from the very beginning, in the EMIT proposal, it was clear we were required to make sure all the EMIT measurements and products were available to all scientists and interested parties who wanted to access those. So let me emphasize, all of EMIT data are going to NASA's Land Processes DAC, where anyone listening to this can access and download those. They aren't there quite yet because we have to get valid products into the DAC, but all of EMIT measurements will be available for investigators to pursue whatever avenue they think that is worth pursuing. So we're absolutely committed. And that's actually part of NASA's new thrust in open science. The Earth Science Division and the Science Mission Director at NASA have a strong priority to make sure that our algorithms, everything we do with EMIT, our calibration, is accessible by everyone so they can learn from it and they possibly can help us improve it. So we're absolutely working to make sure our measurements and our approach to processing those measurements are open to everybody to examine and take advantage of as we all try to move forward our understanding of this planet.
So, David, is that a task that maybe you have to really, really own? I know that you worked a lot on the actual, instrumentation and the software behind how these data are coming in, but ultimately, this has to be something that's packaged and delivered and accessible to, as Rob is mentioning, to so many different scientists that may want to get their hands on this. So how are you approaching that? Taking these data, there's going to be a lot, and organizing it, putting it together, displaying it in a fashion that can be used by the science community.
Yeah, it's a great question, and I think we can divide that into two parts. There's the data itself, which will be handled by the NASA Digital Archive. And so we have a lot of help there from our colleagues at the archive to help format the data and distribute it in a user-friendly format. And then there's the code on the other side. Rob talked about us making our algorithms open as well. And here I think EMIT really differs from a lot of the missions that have come before. We're pretty progressive, actually, in our use of open source, to the point where we've actually developed our code when the EMIT mission was still in formulation and development in an open source environment, meaning that any university student who wanted to could go onto GitHub and download our entire science data system in whatever state it was in and try and reproduce that analysis on their own with all the associated data. So this is quite radical, actually, and has really helped us. So it wasn't actually a burden at all. We did, of course, need to do some documentation so that our code was actually usable and legible to people who weren't a part of the team. But it helped us far more than it was a burden in that other folks were able to use our code for other purposes. We've talked about other imaging spectrometers for airborne campaigns and other kinds of campaigns that could use these same algorithms in their data, which we consider to be best of class. And they've found things that we wouldn't have found. So there are minor issues and bugs that other folks have found because we had more eyes on that code base, more people using it in a broader user community contributing. We were able to actually move forward much more quickly, I think, than otherwise. And it also benefits, I think, for EMIT's legacy, the eventual use of this code by other potential space missions and other individuals who want to use it for their own ends. So it really is the property of everybody, all of the taxpayers who have funded EMIT algorithm development, and we want it to be accessible to those people.
I want to sort of end with a certain idea about why we do what we do, because you both seem very passionate about this and very excited, right? And I think I'm catching you at just the right time, right? Because it's just that you've already made these maneuvers, and the data is going to be coming in real soon. Of course, you got to make those tweaks, but this is just a very exciting time. But if you pull back and think about the opportunities that NASA's bringing to the science community to have the opportunity to, get the funding to build such an instrument and put it on a place like the International Space Station in low Earth orbit, and observe and continue to do science and observe things. I think both of you maybe have a good understanding being in this world as to why we do what we do, why we go to space, why we study different planets, and including our own, and add to the scientific community these data that can contribute to a better understanding of Earth and even different planets, right? Both of you have studied not just the Earth, have studied other planetary bodies in the solar system. And I wonder what sort of drives you. Rob, if we can start with you, just sort of, if you think about what drives you and what inspires you to continue to pursue some of the things that you're pursuing and why you think it's important.
Yeah, so great. Two parts. Why it inspired me, I guess. I grew up in a family with a scientist as a father, so I've been always clear that the scientific method is amazing in what it's allowed us to move forward in our entire society, and the technology that we're all taking advantage of, including this one, build on science and discoveries of testing hypotheses, trying to falsify them, then showing that we can't falsify this one, so let's use it to go forward. That goes on forever. And right now we're in an amazing age in space science in particular, where we can look outward to exoplanets with spectrometers. We can look through our solar system with spectrometers and other tools. And then we can look at our planet, which is just rich with spectral signatures that offer a host of new science hypotheses to test, whether it's related to biodiversity, algal blooms, snow albedo, mineral dust, methane in the atmosphere, that we do better as a society when we have evidence to base decisions on. And so science, in some sense, is a way to collect evidence, test, make sure it's real evidence, and then make good decisions going forward. So I'm inspired at all those levels, but clearly discovery, seeing something for the first time that no one, in some cases, expected, water at low latitudes on the moon, methane point sources, as David described, it was his algorithms that did it in four corners. That's inspiring. And then, of course, the benefit to society is that we have good new information to make good new decisions as we go forward. And of course, that's incredibly fulfilling as well.
Amazing. David, I'll pass to you for the same question, sort of what inspires you and how your perspective on why what we do is important.
Sure. Well, I'd first echo everything that Rob said. I agree that information has this power to help humanity in an apolitical way. It's just a uniformly good thing to have more information about how our planet functions, particularly in this age. So I think that's critically important for me. But I also see a shift underway in the way that we look at the planet. Computers have become powerful enough that they can start to be partners in this exploration of Earth and other planets. And these information machines, including imaging spectrometers, are now being deployed along with the help of powerful computers to measure our planet in dramatically new ways. And we've seen this reflected as well in a shift in priorities for the coming decade. NASA has slated a new Earth System Observatory that includes an imaging spectrometer component called the Surface Biology and Geology Investigation. And this will be an imaging spectrometer similar to EMIT, but that will cover the entire Earth terrestrial area and coastal aquatic zones every 2 weeks or so. And so a dramatic new data set that will open new eyes on our planet, new forms of understanding. So this is just one aspect of this fundamental shift that I see in the way that we are observing our planet from space, and I want to be a part of that.
That's what I love about the scientific community. I get to have a lot of you guys on the podcast, and it's just it seems like you always want more in like a very positive way. You know, it's just we're contributing, we're learning a lot, but there's always more. You know, there's more to do, and that level of excitement and that level of passion in the continuous pursuit of more knowledge and more science is just it's just inspiring to me, and I hope it is to our listeners as well. Rob and David, thank you so much for coming on Houston. We have a podcast. This was very enlightening to learn about EMIT and everything that's going on, and having you both on and your wild expertise in spectroscopy and some of the things that you're contributing to this mission. Wishing you the best of success and all the great things that EMIT is going to bring the scientific community. Thanks for coming on.
Well, thank you so much. It's been a tremendous pleasure.
Houston, go ahead.
Stop of the space shuttle.
Roger, 0J, and I feel fine.
Shuttle has cleared the
Became
tower.
a feast for all mankind.
It's actually a huge honor to break a record like this.
Not because they are easy, but because they are hard.
Never Houston. Welcome to space.
Hey, thanks for sticking around. Really a pleasure talking with Rob and David today about EMIT, and learned a lot about what they're doing and how we're studying the Earth, that perspective from the International Space Station. Some great stuff. You can check out more at nasa.gov/ISS to check out this experiment and many of the others that are happening aboard the orbiting complex. Of course, we are one of many NASA podcasts across the whole agency. You can check them all out at nasa.gov/podcasts. It's there that you can find our entire collection. We even have other collections that we've split up into different episodes. We have a space station collection if you want to check out more of some of the research. We dive into a lot of specific experiments that are happening aboard the space station in many of our episodes, and you can check them all out, again, in no particular order. On social media, you can talk to us on the NASA Johnson Space Center pages of Facebook, Twitter, and Instagram. Just use the hashtag AskNASA on your favorite platform to submit an idea or ask a question for the show. Just make sure to mention it's for us at Houston. We have a podcast. This episode was recorded on August 9th, 2022. Thanks to Will Flato, Pat Ryan, Heidi Lavelle, Belinda Polito, and Jaden Jennings. And of course, thanks again to Rob and David for taking the time to come on the show. Give us a rating and feedback on whatever platform you are listening to us on, and tell us what you think of our podcast. We'll be back next week.
This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, and to find out how you can volunteer, please visit LibriVox.org. Recording by Tom Yates. TomInBKK.com.
The Black Cat by Edgar Allan Poe. For the most wild, yet most homely narrative which I am about to pen, I neither expect nor solicit belief. Mad indeed would I be to expect it, in a case where my very senses reject their own evidence. Yet mad am I not, and very surely do I not dream. But tomorrow I die, and today I would unburthen my soul. My immediate purpose is to place before the world, plainly, succinctly, and without comment, a series of mere household events. In their consequences, these events have terrified, have tortured, have destroyed me. Yet I will not attempt to expound them. To me they have presented little but horror. To many they will seem less terrible than baroques. Hereafter, perhaps, some intellect may be found which will reduce my phantasm to the commonplace, some intellect more calm, more logical, and far less excitable than my own, which will perceive, in the circumstances I detail with awe, nothing more than an ordinary succession of very natural causes and effects. From my infancy I was noted for the docility and humanity of my disposition. My tenderness of heart was even so conspicuous as to make me the jest of my companions. I was especially fond of animals, and was indulged by my parents with a great variety of pets. With these I spent most of my time, and never was so happy as when feeding and caressing them. This peculiarity of character grew with my growth, and in my manhood I derived from it one of my principal sources of pleasure. To those who have cherished an affection for a faithful and sagacious dog, I need hardly be at the trouble of explaining the nature or the intensity of the gratification thus derivable. There is something in the unselfish and self-sacrificing love of a brute which goes directly to the heart of him who has had the frequent occasion to test the paltry friendship and gossamer fidelity of mere man. I married early, and was happy to find in my wife a disposition not uncongenial with my own. Observing my partiality for domestic pets, she lost no opportunity of procuring those of the most agreeable kind. We had birds, goldfish, a fine dog, rabbits, a small monkey, and a cat. This latter was a remarkably large and beautiful animal, entirely black, and sagacious to the astonishing degree. In speaking of his intelligence, my wife, who at heart was not a little tinctured with superstition, made frequent allusion to the ancient popular notion which regarded all black cats as witches in disguise. Not that she was ever serious upon this point, and I mention the matter at all for no better reason than it happens, just now, to be remembered. Pluto, this was the cat's name, was my favorite pet and playmate. I alone fed him, and he attended me wherever I went about the house. It was even with difficulty that I could prevent him from following me through the streets. Our friendship lasted in this manner for several years, during which my general temperament and character, through the instrumentality of the fiend intemperance, had, I blush to confess it, experienced a radical alteration for the worse. I grew, day by day, more moody, more irritable, more regardless of the feelings of others. I suffered myself to use intemperate language to my wife. At length I even offered her personal violence. My pets, of course, were made to feel the change in my disposition. I not only neglected, but ill-used them. For Pluto, however, I still retained sufficient regard to restrain me from maltreating him, as I made no scruple of maltreating the rabbits, the monkey, or even the dog, when by accident or through affection they came in my way. But my disease grew upon me, for what disease is like alcohol? And at length even Pluto, who was now becoming old, and consequently somewhat peevish, even Pluto began to experience the effects of my ill temper. One night, returning home, much intoxicated, from one of my haunts about town, I fancied that the cat avoided my presence. I seized him, when in his fright at my violence he inflicted a slight wound upon my hand with his teeth. The fury of a demon instantly possessed me. I knew myself no longer. My original soul seemed at once to take its flight from my body, and a more than fiendish malevolence, gin-nurtured, thrilled every fibre of my frame. I took from my waistcoat pocket a penknife, opened it, grasped the poor beast by the throat, and deliberately cut one of its eyes from the socket. I blush, I burn, I shudder while I pen the damnable atrocity. When reason returned with the morning, when I had slept off the fumes of the night's debauch, I experienced a sentiment half of horror, half of remorse, for the crime of which I had been guilty. But it was at best a feeble and equivocal feeling, and the soul remained untouched. I again plunged into excess, and soon drowned in wine all memory of the deed. In the meantime the cat slowly recovered. The socket of the lost eye presented, it is true, a frightful appearance, but he no longer appeared to suffer any pain. He went about the house as usual, but as might be expected, fled in extreme terror at my approach. I had so much of my old heart left as to be at first grieved by this evident dislike on the part of a creature which had once so loved me. But this feeling soon gave place to irritation, and then came, as if to my final and irrevocable overthrow, the spirit of perverseness. Of this spirit philosophy takes no account. Yet I am not more sure that my soul lives than I am that perverseness is one of the primitive impulses of the human heart, one of the indivisible primary faculties or sentiments which give direction to the character of man. Who has not 100 times found himself committing a vile or silly action for no other reason than because he knows he should not? Have we not a perpetual inclination, in the teeth of our best judgment, to violate that which is law, merely because we understand it to be such? This spirit of perverseness, I say, came to my final overthrow. It was this unfathomable longing of the soul to vex itself, to offer violence to its own nature, to do wrong for the wrong's sake only, that urged me to continue and finally to consummate the injury I had inflicted upon the unoffending brute. One morning, in cool blood, I slipped the noose around its neck and hung it to the limb of a tree. Hung it with the tears streaming from my eyes and with the bitterest remorse at my heart. Hung it because I knew that it loved me, and because I felt it had given me no reason of offense. Hung it because I knew that in doing so I was committing a sin, a deadly sin that would so jeopardize my immortal soul as to place it, if such a thing were possible, even beyond the reach of the infinite mercy of the most merciful and most terrible God. On the night of the day on which this cruel deed was done, I was aroused from sleep by the cry of fire. The curtains of my bed were in flames. The whole house was blazing. It was with great difficulty that my wife, a servant, and myself made our escape from the conflagration. The destruction was complete. My entire worldly wealth was swallowed up, and I resigned myself thenceforward to despair. I am above the weakness of seeking to establish a sequence of cause and effect between the disaster and the atrocity, but I am detailing a chain of facts and wish not to leave even a possible link imperfect. On the day succeeding the fire, I visited the ruins. The walls, with one exception, had fallen in. This exception was found in a compartment wall, not very thick, which stood about the middle of the house, and against which had rested the head of my bed. The plastering had here, in great measure, resisted the action of the fire, a fact which I attributed to its having been recently spread. About this wall a dense crowd were collected, and many persons seemed to be examining a particular portion of it with very minute and eager attention. The words strange, singular, and other similar expressions excited my curiosity. I approached and saw, as if graven in bas relief upon the white surface, the figure of a gigantic cat. The impression was given with an accuracy truly marvelous. There was a rope about the animal's neck. When I first beheld this apparition, for I could scarcely regard it as less, my wonder and my terror were extreme. But at length reflection came to my aid. The cat, I remembered, had been hung in a garden adjacent to the house. Upon the alarm of fire, this garden had been immediately filled by the crowd, by someone of whom the animal must have been cut from the tree and thrown, through an open window, into my chamber. This had probably been done with the view of arousing me from sleep. The falling of other walls had compressed the victim of my cruelty into the substance of the freshly spread plaster, the lime of which, with the flames and the ammonia from the carcass, had then accomplished the portraiture as I saw it. Although I thus readily accounted to my reason, if not altogether to my conscience, for the startling fact just detailed, it did not the less fail to make a deep impression upon my fancy. For months I could not rid myself of the phantasm of the cat, and during this period there came back into my spirit a half-sentiment that seemed, but was not, remorse. I went so far as to regret the loss of the animal, and to look about me among the vile haunts which I now habitually frequented, for another pet of the same species, and of somewhat similar appearance, with which to supply its place. One night as I sat, half stupefied, in a den of more than infamy, my attention was suddenly drawn to some black object, reposing upon the head of one of the immense hogsheads of gin, or of rum, which constituted the chief furniture of the apartment. I had been looking steadily at the top of this hogshead for some minutes, and what now caused me surprise was the fact that I had not sooner perceived the object thereupon. I approached it, and touched it with my hand. It was a black cat, a very large one, fully as large as Pluto, and closely resembling him in every respect but one. Pluto had not a white hair upon any portion of his body, but this cat had a large, although indefinite splotch of white, covering nearly the whole region of the breast. Upon my touching him, he immediately arose, purred loudly, rubbed against my hand, and appeared delighted with my notice. This, then, was the very creature of which I was in search. I at once offered to purchase it of the landlord, but this person made no claim to it, knew nothing of it, had never seen it before. I continued my caresses, and when I prepared to go home, the animal evinced a disposition to accompany me. I permitted it to do so, occasionally stooping and patting it as I proceeded. When it reached the house, it domesticated itself at once, and became immediately a great favorite with my wife. For my own part, I soon found a dislike to it arising within me. This was just the reverse of what I had anticipated, but I know not how or why it was, its evident fondness for myself rather disgusted and annoyed. By slow degrees, these feelings of disgust and annoyance rose into the bitterness of hatred. I avoided the creature, a certain sense of shame and the remembrance of my former deed of cruelty preventing me from physically abusing it. I did not for some weeks strike or otherwise violently ill-use it, but gradually, very gradually, I came to look upon it with unutterable loathing, and to flee silently from its odious presence as from the breath of a pestilence. What added, no doubt, to my hatred of the beast was the discovery, on the morning after I brought it home, that, like Pluto, it also had been deprived of one of its eyes. This circumstance, however, only endeared it to my wife, who, as I have already said, possessed in a high degree that humanity of feeling which had once been my distinguishing trait, and the source of many of my simplest and purest pleasures. With my aversion to this cat, however, its partiality for myself seemed to increase. It followed my footsteps with a pertinacity which it would be difficult to make the reader comprehend. Whenever I sat, it would crouch beneath my chair, or spring upon my knees, covering me with its loathsome caresses. If I arose to walk, it would get between my feet and thus nearly throw me down, or, fastening its long and sharp claws in my dress, clamber in this manner to my breast. At such times, although I longed to destroy it with a blow, I was yet withheld from so doing, partly by a memory of my former crime, but chiefly, let me confess it at once, by absolute dread of the beast. This dread was not exactly a dread of physical evil, and yet I should be at a loss how otherwise to define it. I am almost ashamed to own, yes, even in this felon's cell, I am almost ashamed to own that the terror and horror with which the animal inspired me had been heightened by one of the merest chimeras it would be possible to conceive. My wife had called my attention more than once to the character of the mark of the white hair of which I had spoken, and which constituted the sole visible difference between the strange beast and the one I had destroyed. The reader will remember that this mark, although large, had been originally very indefinite, but by slow degrees nearly imperceptible, and which for a long time my reason struggled to reject as fanciful, it had, at length, assumed a rigorous distinctness of outline. It was now the representation of an object that I shudder to name, and for this, above all, I loathed and dreaded, and would have rid myself of the monster had I dared. It was now, I say, the image of a hideous, of a ghastly thing, of the gallows. O mournful and terrible engine of horror and crime, of agony and of death! And now was I indeed wretched beyond the wretchedness of mere humanity, and a brute beast whose fellow I had contemptuously destroyed, a brute beast to work out for me a man fashioned in the image of the high God, so much of insufferable